Hello, good morning to everybody. Okay, so we now continue with the second slot of the session, Advances in Remote Sensing Methods, Techniques and Products. We have 5 presenters this morning. We're going to start with Preiman Seimian from University of Stuttgart. And worth noting that in order to keep track of time, we're just gonna give a short signal when you're 17 minutes, so that you can decide if you want 3 minutes for questions or continue with your presentation. Okay, thanks.
So good morning, everyone. My name is Preiman Seimian from University of Stuttgart, Institute of Geodesy. Today, I'm happy to present our work here, one of our work that we wanted to reconstruct our hindgas GRACE data back in time and get a longer time series for total water storage anomaly. Let's get started. I start with the general introduction. So most of you have seen this nice plot from USGS, and you know already that you can divide the water in the water cycle into two important parts, pools and fluxes. And in pools, you can store water. So what I mean is you can store water in terms of surface water, groundwater, soil moisture, glaciers, and also iceberg. And if you add them up together, you get a variable that is called total water storage. And it's really important variable, which is one of the essential climate variables. But it's really hard to estimate that. Until 2002, that the GRACE launched, and it was a satellite, most of you know, the collaboration between DLR and NASA. And the aim of this satellite was to estimate the gravity change at monthly scale with high precision. And it's at height of 500 kilometers with a distance of 200 kilometers between two satellites. And as you can see, there are two satellites. They call them Tom and Jerry. The concept is quite simple. You have one satellite that sees the mass. It's really attracted by the mass, and the distance would change. If you can measure the distance precise enough, then you can change it to the change of gravity, and gravity is related to mass. At the scale of monthly change, you can assume that this is water change. With 1 day, you get the figure on the left. With 1 week, that would be the track that you can cover with GRACE, and with monthly, you can cover the whole Earth. So the data is at monthly scale, and as I said, it was launched in 2002, and the successor of GRACE launched in 2018 with a year gap. It's a really successful satellite mission. People started to use it for many, many different applications. But I would like to talk about one of the important things about GRACE, which is the short record of data. So you have data from 2002, around April 2002. And if you consider GRACE follow-on and forget about the gap, you can have the data for 20 years. And I would claim now that this time period is not enough for climate assessment. And I would try to convince you with this slide. So imagine that I would take all Januaries, take the average, and then do it for all months, and you get something that we call climatology, so monthly mean. And to see that this climate change climatology signal is related or sensitive to the time period of data, let's take a longer time period of data from a model and divide it into 2 time periods. So the GRACE time period and the time period before GRACE. So we have now data from 1980. It is recommended that if you want to calculate this climatology, the data should be at least 30 years of data, or favorable 60 years of data. But here we have 20 years. So let's see if we take the climatology or this monthly mean from each of these time series, what would be the consequences over the world. We took some basins, and we calculated this climatology for different time period. As you can see, for example, in Tigris or Amazon or to some extent OP, there are not that much different between different time periods. So you are safe to say that if you get the time series of grace, you are estimating the right or correct climatology. But clearly it's not the case for Mississippi, Death Valley, or Mirror Downing in Australia. So this means that if you take the only time period of grace, you are underestimating or overestimating something that we call climatology. So the grace time period is short. What we can do to extend it or hindcast it back in time? We propose to use models. So before grace, a lot of studies try to estimate total water storage anomaly using models. You can divide them in different groups. Here I show them in 3 groups, so global hydrological models, land surface models, and also reanalysis models. And the question is how accurate they are. So if they were so accurate, why we launched GRACE? So let's take a look at the trend of these models and compare them with GRACE. So this is the trend we calculated over the globe. And on top, you can see 3 different products of GRACE, 2 mass cones, 1 spherical harmonic solutions. And there are 13 other models that we have included here. Just take one example here in Southern America. So you clearly see a negative trend in this region. In some models, you can see that this trend is represented. So they could also capture. But in some others, they clearly miss this negative trend. Let's take a positive trend in North America. It would be another, again, the same story. So in some models, these models could capture the positive trend, but in some models, still they are lacking this intensity of the trend. So this means that you cannot trust one single model for the globe. Maybe in your region or in your specific area of interest, one model would perform the best, but it doesn't mean that it would be over the globe. So we propose that we should combine these models to get the benefit from them. To combine such a different time period, different models, one thing that comes to our mind is take the average of them, so ensemble mean. So this is the first method that you can maybe use. The second thing we already mentioned that these models have different performance. So let's get more weights for the ones that they have better performance and have a weighted mean. You can use different weights. Here we have used the difference, inverse of the difference between the RMS of the signal. And this is the result that you can get from GRACE and also these models if you just use ensemble mean or ensemble weighted mean. So you can see the light blue is the time period of GRACE, and the time period of and the time series that is captured from the ensemble mean in blue, and in green you can see the ensemble weighted mean. So for example, just take the case Tigris. So maybe the RMS of the signal is represented, but clearly you can see that the trend is not captured by the ensemble mean. In OP, maybe you can say that the ensemble mean or ensemble weighted mean is good enough comparing to GRACE. There are some other examples. For example, in Amazon, you clearly see that the RMS of the signal is missing. So take these 2 methods, and these are the benchmarks for us. This is our now naive methods, and try to do better. We could use multivariate linear regression. So you put some weights and try to optimize these weights in order to get the best combination of them. Or you might say that I would like to have only positive weights. So the method is called non-negative least squares. And you can include some machine learning methods. So support vector machine, random forest, decision tree, and also Gaussian process regression. And we need to validate the performance of these models. And we validate over different time period. Over the time period of GRACE, we use GRACE as a validation data set. For the time period before GRACE, we use the data set developed at Bonn, which is SLR, satellite laser ranging. And this is the performance of these data sets. So you see the correlation of the SLR and GRACE over different basins. As you can see, it's not perfect in some regions, so we put the threshold of 0.8, and this is the result. So we just compared the results over these basins that we know the quality of the data is good enough. So this is the results over grace. This is one metric I show. I included more, but here I just show the KGE. To have a better visual sense of the data of KGE here, I put the gray scale for the negative values, and we wanted to have better KGE, so this is the base. This is the performance you get after applying ensemble weighted mean, non-negative least squares, and also the MLR. So clearly you can see that with the ensemble weighted mean and non-negative least squares, you might improve this performance in some regions, for example, with the non-negative least squares in Australia, but still there are many basins that they have negative KGE. But with the MLR, which is not a really complex model, you can really do a good job in most of the regions. So the KGE is more than 0.8 at least in many of them. And let's take the ensemble mean and this MLR as the best that we have got so far, and compare the machine learning methods. So these machine learning methods, some of them are really heavy for computations, for example, GPR, but some of the others not. So for SVM and random forest, you can see that you can improve the performance a lot, but there are still some basins that the performance shows the KGE of negative, which is not favorable. But with decision tree, you can push this performance to the better KGE or positive KGE. And finally, with GPR, you get most of the regions really high quality. So if you want to compare them in a better perspective, I would say figure, I like this plot with the CDF. So the one that is on the right of the plot, on the bottom right, it would be the best. So in that case, GPR is the best, following by MLR. But the good thing about this is with the simple model like MLR, you can get performance that is near to the GPR, which is really complex model. And we have done this analysis here, I should say over basins, I presented here, but we have done the same over pixels as well. And I showed the results excluding Greenland and Antarctica. And let's see what would be the performance over with SLR. So these are the correlation that you can get from the basins with comparing the time period of 1992 to 2012 with SLR. These are the naive methods. We wanted to do a better job. So with the simple non-negative or MLR, you can see that MLR do a better job and improve the result tremendously. And with the machine learning methods, you can clearly see that GPR is doing the best. And among these machine learning methods that are not heavily computational, random forest do a better job with the SLR. And this is the comparison over the time period of grace, only the time period of grace. And this means that we can include grace as well. So you can see here that here is grace with the highest correlation, but GPR and MLR can do a really good job comparing to that. So for the outlook, we want to include models that include Greenland and Antarctica. Many of the models that I presented today, they have not a good quality over these two regions. The other thing is we wanted to validate our estimations or results with more validation data sets, including, for example, GPS stations, vertical motion, or some proxy data, for example, soil moisture, or in general state variables, or you can try to use fluxes, precipitation, or the others back in time to see that if the performance is the same during the time period of grace and also before grace. And the next step would be if you have this longer time period of data back in time up to 1980, maybe you want to do some climate assessment. So we already have used it for drought characterization, which is really important, the time period that you get as your base, your climatology. So we already use that. So for more application, we are trying to use this data set. As recommendation, I would say that The data record of GRACE is short. I hope I have convinced you with that slide that it might be dangerous to use it for some regions. Don't use this GRACE data like trend of GRACE only for a short time period from 2002. A single model would not do a good job over the whole globe. So if you use any type of research that use only one model, just be aware that maybe your model is not the best for that region or globally. And the last one is there are some existing models, so let's use them. Here we have shown some methods that you can combine them. You can use your own methods to combine these models and get your combination or reconstruction back in time. Thank you very much.
Okay. Thank you very much for this nice presentation. We have time for one or two questions from the audience.
I can ask a question.
Yeah, sure.
Okay, or maybe I have two questions. The first one, when you apply the machine learning techniques, are you just doing pixel analysis, or are you also taking into account the surrounding patterns of the pixels?
So here I've shown the results over basins, but for the pixels only we take the results of one pixel, no surrounding pixels. So, yeah.
Okay, good.
And for each model is developed for each pixel, so pixel-wise.
Okay, right. And the second one is, so you're doing this analysis for total water storage, TWS, right? Could you also expand it to do particular components of the water cycle, such as evapotranspiration, runoff, or do you see that feasible with this method?
It's feasible, but I would say that it's hard to incorporate the uncertainty. So here I haven't shown the uncertainty. So for each of these models, you can get also the error. I expect that the error would be higher if you include one compartment, because you have one compartment, you have other compartments that they own uncertainty. If you add them up, then the results for one compartment have a really huge uncertainty. So you can get evapotranspiration, but the problem with that would be the uncertainty of the data.
I have a question regarding, like you said, the use of GPS. Have you tried that?
Not yet. We have tried it over one region, Amazon, but not over the globe. So the next step would be to include that, only vertical motion, of course. And one note, maybe if any of you knows a good model that performs really well over Greenland and Antarctica, just come to me, because I'm really looking for such a model to incorporate in our estimation.
Any other questions? Okay, so if not, thank you very much, and we'll move to the next speaker, who is Jean-François Créteau from Lagos, and he will speak about like long-term lake variation from satellite related climate analysis.
Good morning. So I'm Jean-François Créteau from Lagos. I'm the project scientist of a project which is funded by ESA, which is under the program Climate Change Initiative, and the project is about the lake studies. So we are trying to set up a database of multivariable in order to understand the role of lake in the climate. And the team is there's a list of teams in Europe that are listed here, all of my co-authors from different countries in different laboratories in Europe and also in Canada. So why are we studying lakes? So there is a very interesting paper, famous paper in 2009, I think, from Williamson, who stated that lakes, they are sentinel, integrator, and regulator of climate. So it means that many lake hydrological and physical variables are potential indicators of current climate change. So that's the first point. Second point, also the lake the presence of lakes regulate the climate regionally or globally, so they are also a role in the climate. And also they are integrator of climate change because they store in their sediment some kind of archive of the past climate. So these are the three main points. And of course, the climate is interacting a lot with lakes and alter also the biophysical and the hydrological variables on lakes. So what we are trying to do is what are the linkage between lakes and climate first, and are this linkage measurable from satellites? So there are millions of lakes, from a small one to very big one. And these lakes are of a great interest in different disciplines like climatology, of course, hydrology, limnology, etc., etc. And this is an interesting project for us because it's also a cross-disciplinary project with different teams from different who are looking at from different perspectives. So what is the database? So we are building a database. We are setting up a database on 2025, the largest lakes. The interesting point is really that we are trying to have different variables. It's a response to the GCOS implementation plan, sorry, to have the essential climate variable. And we have 6 essential climate variables in this project: the lake water extent, lake water level, the lake ice cover, the lake surface water temperature, water leaving reflectance, and lake ice thickness, which is a new variable introduced recently. And it will also include in the future lake volume changes from different satellites for this project. So we also interact a lot with modelers. So we have for that a climate research group, which perform the ECV's product assessments to ensure that the climate modelers have access to the data and in a form, in a shape which is convenient for them and which really tackle the main issues that they want to see from lakes. So this is the project. So now we are going to into detail on each of the variables, not too much, but I will try to show you how we are doing that. So for lake water level and water extent, it's really simple. We are using satellite altimetry in order to measure water level of these lakes with a quite good uncertainty. And for the lake water extent, we are using the simple principle of the building hypsometry. So it's quite I ought to say it's long to perform that because we have to do it for each lake individually, but then it's a very robust method which allows to determine the water level, the water extent of lakes. So we built hypsometry, and from the hypsometry and the water level, then we calculate the water extent. It is shown here. So we have a satellite altimetry time series. We are trying to detect when the water level is high, when the water level is low, to collect some satellite images. We are relying mainly on Sentinel-2 and Landsat. Calculated the water extent of the lakes at this period, and then build the hypsometry, and from the hypsometry again calculate the water extent. So it is done in the project. So this is just an example. I'm not going too much detail in that, but it will be presented by Paul Gibetcom also tomorrow or after tomorrow. It's just an example of time series on lakes of water level in Africa. So we have several lakes in Africa in this database. And the main point that we can see is that it's really interannual variation that are observed in these lakes. And also we see that these internal variations are mainly driven by the precipitation changes, mostly, not only, but mostly. And particularly in East Africa, we see that over the last 2-3 years, there is a very, very big increase, even for the very large lake like the Lake Victoria or Tanganyika, of several meters that are also related to the precipitation changes. So it's how to show also the linkage between lakes and the climate. Now about the lake ice cover and lake ice thickness, how it is calculated. So for ice cover, we have a priori model which is used in order to predict which lakes are supposed to be covered by ice. It's quite simple, but it's important to do that. And then we have a model which is a random forest algorithm trained on manually labeled images, and we feature the retrieval which is determined from MODIS images at the top of the atmosphere reflectance, combining all available data from MODIS and from Aqua and Terra satellite. So here you have two examples of a lake ice cover of the Great Lakes in North America for low ice year and for high ice year. We also calculate the time of the freeze up and the breakup of the ice in these lakes. And for lake ice thickness, the estimates are based on physical modeling of the waveform of satellite altimetry. So it shows a specific signature which is related with the double backscatter of the radar waveform. So this model has been validated on some studied case studies, and now we will develop this method for many lakes, and we will have a presentation by Anna Mangili, also our colleagues in this workshop for this specific method. Lake surface temperature, it is measured from radiometers, which captures the visible and the thermal infrared part of the electromagnetic signals spectrum, and we use moderate resolution images of 1 kilometer resolution. So the temperature of lake is very important. It's really a fundamental characteristics of lake, and it's of course directly related to global warming. We see that there is really on this map a really global increase observed over the last past years, particularly in Europe, and we have also on this graph anomalies of the warm season, which shows that it's particularly marked in the European region. And so the data, of course, the data of the lake surface temperature are distributed in the lake database together with the other data. And it's also not interesting, but it's also remarkable that lake surface temperature, of course, it's consequences of the global warming, but it also has consequences and impact on the lacustrine ecosystem, on the chlorophyll, on the fauna, etc., etc. So this is a very important point. So lake water living reflectance, in other words, it's also what we call more familiarly the water color. It's based on a model also and on medium resolution optical sensors. And it's from the water living reflectance, we can also deduce two very important physical variables that are the chlorophyll A and turbidity that are delivered from this that are derived from this water living reflectance. And what so it has been validated also the method, it is produced, distributed in the database, and so also analyzed, and the analysis of chlorophyll A and turbidity, it shows that the increase mainly happens in the northern hemispheres, while in the Africa, South America, it's more stable, or it's not so evident that there is a trend. So this is another very important variable. In the future, we will have the lake storage change, which is not yet included in the database, but just here an example from a study that we have done with a colleague in Colorado and Lagos on the lake water storage change at global scale. So what the data set we used were Landsat imageries, the radar altimetry, ISAT, also a laser altimetry. We constructed also high frequency lake areas and derived the hypsometry in order to determine the volume change. And the findings of this study are very interesting because it's for the 2,000 biggest lakes and reservoirs. And we have separate arid region and humid region, and also globally. And we have separate reservoirs and lakes. And what we have found is that there are a declining storage over more than 60% of the large natural lakes over the last 30 years, with a rate of 27 gigaton per year. But we see that it's particularly marked in the arid region more than in humid region, and also that it's particularly marked for the reservoir in this region, but that there is a reverse tendency over the last 10 years, which is shown maybe here. We can see that there is an increase over the last years. And for example, the reservoir storage changes increase account for 20 cubic kilometer per year, which represent minus 0.0555 millimeter per year of the global sea level rise. So this is a very interesting study, which showed that it's important to have also storage change in the database. Moreover, we also explore the lake variable because it is interesting in this project is that we have the different variables, and we are trying also to see the consistency and how to do cross validation, cross analysis. And we have some options in the project for that, or use cases that are developed. We are trying to understand the impact of heat wave and storm events on lakes, the water quantity in relation to water quality in a changing environment. And also we are building some climate indicators on the global data set. It's shown here. It's made by the Brockman Consult company in Germany. So they develop a website where we can have different indicators. And some example here of the heat waves and storm events impact on lakes. We did that on the European lakes during the heat wave in 2019. So we measure the chlorophyll A, so we extract the chlorophyll A, and what we observe is that the timing and the magnitude of the response of the heat wave events depend on the lake depths, on the lake's bathymetry. The deeper lake responds sooner, probably because of higher temperature leading to stronger stratification. And in contrast, the shallower lake responds a little bit later with a great response. So after this heat wave, so this is shown in this graph, depending on different groups of lakes, depending on their bathymetry. We also try to understand the linkage between the water quality and water quantity. So here we have done a study on a lake in the Euphrates Basin, so the Qadisiyah Lake. It's a reservoir, in fact, but we will also extend that to all the lakes of the database. But it shows that during La Nina events, it provokes some drought in the region. So the drought provoke, of course, a water level decrease, and it has been immediately followed or immediately consistent with chlorophyll A and turbidity increase. So it's shown on this graph. And of course, the target of the global lakes, we will continue this study. It's very preliminary, but it's very interesting to see the linkage between different variables on lakes. So the future, so we have many ideas for the future of this project. One of it, of course, is to use the new missions, so Trishna for surface temperature. I'm not talking about Trishna now, but Trishna will give surface temperature and lake temperature at very high resolution. So we will use that for the lake surface temperature. And also for lake water level, lake water extent, and lake water storage change, we will use, obviously, the SWOT mission. SWOT is supposed to measure more than 5 million or even almost 6 million of lakes bigger than 1 hectare. Of course, it's much more than what we have in the CCI lake database, but it will be very interesting because it will allow to fill some spatial gaps and so on. And of course, it's interesting because the same mission will give the three variables together. So just examples, you have seen that yesterday already. You will maybe see it in the other days. It's really the extraordinary images, the SWOT images. So here it's in the Yukon Valley in Alaska, and you have thousands of small lakes here. And for all of these lakes, there is access to the water level. We also have the access to the water extent, and we have also some posters that show the performance of SWOT for small lakes in north of France, in south of France, etc. And it's very, very exciting and promising. So the conclusion. So the challenge so this project started in 2019. So it will finish. We are in the second phase, which will finish next year in 2025. So in 1.5 years. And we hope to continue. So the climate change initiative provides a full set of documentation of what is released, what is produced. You have user guide, etc. We use a wide range of sensors. More than 30 sensors are used to construct all the time series for all the variables, as I've shown just in this presentation. So we produce 6 thematic variables over 2024 lakes with 30 years of time series. And for the future, the continuity, we are trying to continue to calculate long-term time series of these variables based on multi-mission. So filling the gaps also, because we have some gaps in the data. So we are trying to fill the gaps. We also always try, of course, I didn't show that too much, but to validate the product. But to validate the product, of course, we need some in situ data. This is not so easy. It's oftenly not distributed. So anyway, we have some in situ data to validate. It has been done, but it's a very important task in our project. We also, very important task of the project is to intensify the cross ECVs analysis. So cross ECVs, I mean, within the project, we have different variables, but also with other projects. CCI project has many different variables to deal with. We will develop new variable, lake surface storage change, lake ice thickness, CDOM, and that will be introduced in the future release. And of course, what will change our vision of that. And the most important is that we are trying always to interact with the climate modelers, so through the climate wizard group. And I think I finished. I don't know if I'm in time, but
Yes, you have 3 minutes, or otherwise we can move into to questions. Are there any questions there in the public? Yes. Please move to the microphone and give your question.
Okay. When you try to make some correlation between lake level and La Nina, for example, did you try to split the population of the lake between the natural one and the monitoring by dams, for example? Because I don't know if it's significant or not.
Of course, well, of course, what I've shown is just an example on reservoirs. So actually, it's really starting study. But of course, then we will split and try to understand, because of course we know that water level is also driven by human action in reservoirs. But yes, of course. And for the water storage change study that we have done, we also have separate both.
Very curious question. Now that you moved into monitoring millions of lakes, it begs the question of what is a lake? How do you define one lake from the other? Or if you keep a topological index of all these millions of lakes that you are monitoring, or for you,
mean for
those are pixels?
Yeah.
Yes. How are you keeping a database of lakes? Do you have a definition of a lake, and do you assign like an ID that I can track?
Yeah, of course. We use the Hydro Lake database, and we also use for SWOT. We are using another database which has been set up by some American colleagues, the CIRCA, and so there is a contour, polygons, etc. of these lakes. So sometimes it's lakes, sometimes it's we have ephemeral lakes, we have temporary lakes, we have reservoirs, we have sometimes it's lakes or wetlands. It's not easy to determine, but all of this is in the a priori database of polygons and so on with ID and so on. Okay.
Okay, thank you. Thank you. So now we move to the next presenter. So the next presentation deals with lake ice thickness. So Anna Mangili could not be here, but a colleague will present for her.
Here you go. Okay, thank you. So Anna sends her regrets. She could not be here. So I'm Claude Duguay. I'm a second author on this slide. And I'll be actually following up a bit on what Jean-François started to introduce. On the one slide, there was ice cover and ice thickness. So I've been involved with some of Anna's work and the retrieval of ice thickness from LRM, low resolution mode altimetry, and then some more recent collaboration on the higher resolution, the SAR mode retrievals. So why, of course, the presentation is just an overview of the key points I will be covering. The first is an overview of lake ice thickness and altimetry, how it's retrieved, the general concept behind it. Then introducing the new approach for the estimation of lake ice thickness from both LRM and SAR mode, which includes the improvement of the estimation and the conclusion and an outlook and recommendations. So lake ice thickness, it is a sensitive indicator of climate change. It's been identified, as Jean-François was showing, as one of the essential, it's a thematic product actually of lakes as an essential climate variable under GCOS. Monitoring, of course, the ice thickness is important from not only from a climate perspective, using that as a signal of changing climate condition at high latitudes, but it also is important for the retrieval of, in some cases, lake water levels, the operation of ice roads, and winter recreation. One big important aspect of this work, of course, is that we're using satellite altimetry to provide it with some definitely better spatial coverage than what is available from in situ observations. Being from Canada, we in the 1980s, 1990s, we had a relatively good network of stations, but now there's only 2 official sites in Canada across the country from monitored by Environment Climate Change Canada that actually monitor ice thickness. And actually the last one, actually there's one that is left this year, Baker Lake. And I will show you actually some results from the retrievals from these 2 lakes. The one that's was monitored for a while is called Great Slave Lake, and then we have Baker Lake. So a few studies have investigated the retrieval of lake ice thickness from altimetry. There's been a bit of work in the past, and about 10 years ago, on the use of passive microwave for the retrieval. But from radar altimetry is relatively new. Justin Beckers from Canada did some work and published in 2017 on the retrieval from Cryosat-2 data. And there has also been some other work that it's touched a bit on the estimation of ice thickness, but maybe mostly in the context of improving the retrievals of lake water levels from altimetry. And that's the 2 other references. Now, there also been, in terms of lake ice thickness retrievals, other approaches have been developed using mostly empirical methods. And the use of empirical methods, we see, establishes statistical relations between in situ measurements of ice thickness or retrieval from a thermodynamic lake ice model and backscatter from the altimeter. And the work here that I will be introduced, the work from Anna, is developing an analytical approach. And the first result from that work on the low resolution mode retrieval was published in TGARS last year. And there's some ongoing work right now on the retrieval of ice thickness from SAR and fully focused SAR. And I will show you some of these results. So the general principle of the retrieval, we're looking at returns from 2 treatise points. Yes, we have, this is in low resolution mode. So as Jean-François was mentioning in the slide, it's looking at double backscatter on the leading edge of the waveform. So a first return, one is from the snow ice interface, and then a second return is from the ice water interface. At KU band, there is penetration. As long as the snow is dry, there will be some penetration. And here in this context, this is for waveform from Great Slave Lake, and you see the track, you see the map and the track on Great Slave Lake, where it's dry conditions, and this consists of clear ice. So I think it's important to say that the method works really well in cold regions, high latitudes, when it's dry conditions, when you have snow on top of the ice, and a clear ice, which we call congelation ice in the ice geophysics. On the right, you see the other waveform is from Sentinel-6 SAR. And here you see double peaks, 1 and 2, which are used then to retrieve the ice thickness from the SAR mode. Here we're looking at Sentinel-6 data. The top panel is for low resolution mode, and the bottom panel is for SAR mode. And you see the differences in the 2 diagram here. And on the right, you see for that a region of interest extracted along the track. You see this example of the first a return at the ice water interface and the return at the snow ice interface. And on the right, this is from the approach that Anna has worked on. You see this is the estimation of ice thickness for that region of interest with a mean of roughly 1.4, 1.33, and the standard deviation of 7 centimeters. And then at the bottom, this is in the SAR mode. So there's an improvement in this case in the retrieval. The mean is close to that of the LRM mode, but there's a decrease in the standard deviation over the retrieval. So there is a improved factor by about 2 with the use of the RTK, the retracker, and for the SAR mode. Now, if we go back to the retrieval, the work that's been published, was published last year on the retrieval from LRM mode, this is using JSON2 and JSON3 data. And we have examples here where you have on the left, these are our MODIS or RADARSAT-2 images. So we overlaid the tracks on top. And along the tracks, what you have, the colors correspond to the ice thicknesses retrieved along the tracks over a section of Great Slave Lake. And so it's doing, there's a slight underestimation, and we'll show you some other graphs, slight underestimation of the ice thickness during the early period of ice formation, where in some cases you may not have any snow on the ice surface. And as you move to the month of February and March, you get some very good retrievals. We've done some comparison against some in-situ measurements as well as simulations with the lake ice model. And at the end of April, you move into melt conditions, and under melt conditions, you don't get a penetration of the KU band signal. It's reflected by the top of the melting snow or ice. And in this case, it results in an underestimation of the ice thickness. And I will show you some other figures about this problem. But overall, under dry conditions over winter, the estimates here, the LIT, the lake ice thickness accuracy estimations were in the order of about 10 centimeters. Now, based on this work, of course, as part of the lake CCI that Jean-François introduced, we're producing longer time series. And to start with, it's only for one lake. So we're starting with Great Slave Lake. And this shows part of the time series. Actually, the time series goes back to 2002. And this product will be released a bit later this year, actually in December next month. And we're looking at here the retrieval of ice thickness from JSON2 and JSON3. These have been compared very recently against some in-situ measurements, but the in-situ measurements tend to be much far away from that track. It's somewhere about 70 kilometers away. So there is, we use that more as a qualitative validation of the retrievals. And then we also perform lake ice model simulations that generate ice thickness on a daily basis and compare those results against the altimetry retrievals. So in general, I would say that the retrievals are very good, except for actually there is this year. So if we look at the time series and we were to pull a trend across this, the part we've done some actually validation of this product. And we found actually that this is, some of these retrievals here are incorrect. And the reason for that's Great Slave Lake in 2019, January, February, we saw that there were large areas along that track where there was no snow on top of the ice surface. And so that resulted in an underestimation of the ice thickness. Later on in the month of, as you move into later months, when the snow starts to accumulate, more snow on the ice surface, then we can still pick up again the lake ice thickness. So this is one case that shows the problem when you don't have any snow on top of the ice surface using this approach. In this case here, we're looking at a comparison between the LRM and the SAR mode. So we've got JSON3 on this graph. We've got JSON3, Sentinel-6 LRM, and then Sentinel-6 in SAR mode. We're looking at comparison of the retrievals. There's good consistency across from the LRM and the SAR mode. And one point which is important here that I mentioned earlier is that when there's any melt occurring on the ice surface, this is what's happening. So we're moving here, there's retrieval, so we're moving for early in the ice season, ice growth, max thickness, and then we get into a melt episode at the time of passage of the satellite. So we got an underestimation ice thickness. Then there's refreezing of the ice surface. And again, we can pick up an ice thickness signal. So these two issues of no snow on top of the ice surface or melt events have an impact. Of course, if along the track there's any open water areas along that track, you could have a mix of ice and open water, and that could also result into an incorrect retrieval of ice thickness. Here we're still looking at Great Slave Lake and then comparing on both the two images from the two dates in more details here, that where we had the melt on the ice surface. And this is taking from radar data, radar image in the background. We had melt, and this corresponds to this. And then by April 18, then we got some refreezing of the surface. And then we get, again, a good estimation of ice thickness. Comparing fully focused SAR and unfocused SAR at 140 Hertz. We have at the top the fully focused in the different months from December. We got February, March, and May. And you can see that neograms, the radograms, sorry, right here, we got the snow ice and the ice water interfaces, and then we got the unfocused UF just at the bottom. And but there's an increase in statistics with respect to the 20 Hertz data. The FF-SAR double peak lit signature is seen at the high resolution. Then when you look at the waveforms over the region of interest, we can see that 140 Hertz, we've got the good fit performances in both cases and consistent lake ice thickness estimation, and also an increase in the accuracy, where we're seeing a decrease, again, in the standard deviation from the histograms. The estimation from high resolution, what you have on top is from the Sentinel-6 unfocus, fully focused SAR, and the SAR at 20 Hertz. And you can see that there's the comparison between the two. And then at the bottom, you have the standard deviation of lake ice thickness estimates over that region of interest. So there are consistency across the three data sets. There's an increased performance with the data higher posting rate at 140 Hertz. And at equivalent posting rate, the fully focused SAR seems to allow better estimations at 20% smaller error bars. Now, this is for Great Slave Lake, all this what I've shown so far, and in the next couple of slides we'll be focusing on Baker Lake. So Baker Lake is another lake in northern Canada. So in the first example, I showed Great Slave Lake, which is related kind of somewhere around here, and then Baker Lake is a lake situated there. And it's a smaller lake, so it's testing whether the retrieval is possible over smaller lakes. Great Slave Lake, by the way, it's somewhere in the order of size of 200 kilometers by 100 kilometer in size, so it's a very big lake. This one we're moving to, we see the track, we're 37 kilometers. And comparison again with the JSON, in this case it's JSON 3, Sentinel-6 in both LRM and SAR mode. We see some good retrievals, but we also see that there's some cases where there's melt occurring at the surface, then we get this underestimation of ice thickness, and then when it refreezes again, we can pick up ice thickness. This other example also from Baker Lake, where we're comparing here the UF-SAR 140 and the fully focused SAR at 140 and SAR at 80 Hertz. And general trajectory of evolution of ice thickness from ice onset about maximum ice thickness is well captured, but as we get some melt, it's underestimation, and then as it refreezes, we come back to a good estimation. So conclusion. So first, lake ice, of course, the thickness is important to monitor for climate change purposes. There's been some papers published from field measurements that have shown that, especially if you look at maximum ice thickness each year, it provides, it's a good indicator of climate change and, of course, climate variability. In ESA-CCI lakes, which focuses on the low resolution mode, there was an approach that was, a retractor was developed, and now it was applied to Great Slave Lake for a short period of time, but now it's being extended, and the data will be released in December for the period 2002-2022, so it's a 20-year record. And as part of S6J Tech's project, which I'm not involved in, and this is one of Anna's project, she is also looked at applying the retractor to SAR mode, and the result that we saw here on the graphs showed that there is good potential as well for the retrieval on smaller water bodies. Outlook and recommendations. So there's a full processing chain has been developed now. It's been implemented as part of Lake CCI, and it's being used operationally for one lake so far. But I mentioned, I made this point about cold regions and lakes. When you have dry conditions, clear ice, congelation ice, it works well. The big test is going to be moving that to lower latitudes where ice composition, we don't have only clear ice, but sometimes you have snow ice formation, bubbly ice layers. So the composition of ice is different. And you get also some episodes where the snow mass is large enough to depress the ice below its hydrostatic level, and you get cracks and get flooding at the base of the snowpack, refreezing. So periods where you have slush at the ice-snow interface and then refreezing of that layer, and that may complicate the retrievals. There may be some increases on definitely uncertainty in those retrievals. There's another project I think that Anna's involved in. It's with development of a tracker lit retrieval for the Crystal mission, so Clé-to-Ver. There's definitely a few other points I added to these slides, is that there's definitely the need for the retrieval of snow depth over lake ice. This has been a topic that people have been mentioning. This is important to retrieve, especially if we want to run lake ice model, two-dimensional over lakes. We need some good information, spatial distribution of snow over the ice surface, and there hasn't been anything yet published on that topic. There's also concurrently, there's also the need to do radio transfer model experiments. So there was a study from ESA, funded by ESA called EM, which integrated now a modeling framework, a combined modeling framework that includes the snow microwave radio transfer model of Ghislain Picard, was published, and our thermodynamic lake ice model. So it's coupling the two together, and then we can run some simulations, different scenarios at different frequencies, different ice conditions. I was talking about snow ice and so on. So we can simulate actually backscattering and waveforms. At the moment, it's in LRM mode only, but there has been interest shown by also even the Crystal mission for integration of the SAR mode in the simulation. So this is something we're really interested in further developing. And finally, there is the need to develop and test operational machine learning, deep learning approaches, algorithms to classify open water, ice types, and so on. We found that with the LRM and SAR retrieval of a lake ice thickness in the early season, sometimes we underestimate the ice thickness. When there's any melt occurring, we underestimate ice thickness. And if there's any open water, mix of ice and open water, then it creates a problem. So in that respect, there's some work that's been done by Jayashri Muguntan. She has a poster ID 20, where she applies machine learning, deep learning approaches to detect open water, young ice, growing ice, and melting ice along tracks of satellite altimetry. And at this point in time, I think the poster is on SAR mode, but she's now extending that into the LRM mode as well. So thank you very much.
Thank you. So we have time for a few questions.
Yes.
Well, first, very nice results, and you and Anna make it look so easy to get these lake eye thickness from Sentinel-6. That's maybe also a good show for Sentinel-6. Two things. You clearly say that you have a problem with melt on the ice. Could you detect the melt also, for example, from the peakiness parameter that's at least in the LRM, and maybe not be working so well in SAR?
Right. So from the SAR, actually, the poster by Jayashri I was mentioning, the poster ID 20. So she's applied to Sentinel-3 SAR mode, and actually she's derived five waveform parameters. So peakiness and the different parameters along the waveform, and she's used that into machine learning algorithm. She showed actually random forest algorithm is providing the best retrievals. So that's the way. Is that?
Yeah, well,
answer your question?
Particularly to mark those outliers where you have the melt and you suddenly have a clearly wrong lake ice thickness. There should be a way to detect those.
Right, actually, so the algorithm does detect when there's any melt occurring. This algorithm, this machine learning approach, detects when there is melt. So, basically, this poster, if you go and look at it, it's going to be. It suggests basically that this could be used as a pre-processing tool to basically detect along, and it shows detect with its melting ice, growing ice along that tracks.
Yeah.
And then you can provide this information to people who are retrieving lake water level and ice thickness.
Yes.
And tell them little flags saying that careful here.
Yes, that's what I
Very
was
likely, yep.
aiming at.
Yes.
And regarding the young ice and well, probably on lakes you won't have multi-year ice.
Mhm.
There were already some studies done also with using the radiometer data from the time of ES2 and Envisat. I think it was Nantan and Civil Labo. So that might be wanting to also look at the radiometer, particularly in Sentinel 6 with the high resolution radiometer, might be able to give you even more extra information.
Yeah, we actually tried we've looked at some of the passive microwave retrievals from altimetry, the combination of passive, active, and see recent publications, and using just the 5 waveform parameters. And even looking actually in the poster also covers the aspect of retrieval from a deep learning CNN, convolutional neural network, recurrent neural network to detect, just looking at the waveform itself, just from SAR, and accuracies that are achieved on the order of 93%, 95%, and so on. The issue, of course, with the passive microwave radiometer is the footprint. So you're looking at tens of kilometer footprints combined with your...
Yeah, but that's why I was mentioning the high resolution one on Sentinel 6, which has channels even up to over 100 gigahertz.
Oh, okay.
Those have much smaller footprint.
Yeah.
So there might be in the higher channels something for you.
Right.
As well. Just to look at.
No, my mind was in the 1937 gigahertz channel.
No.
Okay, thank you very much. We now move to the next presenter, Felix Girard, who's going to talk about the water storage in shallow lakes.
Okay, so thank you for giving me the opportunity to have this talk. And I want to also thank the different co-authors that contributed to this work. This work has been done in the frame of my PhD that is co-hosted at Géosciences Environnement Toulouse and CLS, and that is co-founded by CLS and the Occitanie region. And we'll focus on the comparison of existing methods to derive the height area relationship of shallow lakes in West Africa in order to estimate the volume changes. So thank you also to Jean-François for having introduced a little bit the context related to lakes and volume changes, and also related to hypsometry. Just a few words to say that monitoring lakes volume changes is important because the ecosystem services provided by lakes are modulated by their water storage. And these water storages are changing nowadays, as you can see with the recent study mentioned by Jeff, that stated that over the past 3 decades, more than half of the largest global lakes have shown a significant decrease. Also, a quick context about how we measure volume changes with remote sensing. So to go quickly, we use a combination of water surface heights and area measurements. And there are multiple methods to compute the volume changes. One of the methods is to use the height area relationship, which is also called the hypsometric curve. And it has multiple advantages, such as, for example, getting rid of some lake morphology assumptions, or, for example, using only one variable, so either the height or the area, to compute the volume changes. And the volume changes are, with the hypsometric curve, they are computed by integration of the curve between 2 consecutive height measurements. About the methods we used, so there are multiple methods to derive the height area relationship, and few studies compare these methods with recent remote sensing data. So this is the work we've been doing, and here we propose a comparison of 4 of these methods. The first one, we call it the DEM method, and it basically consists in filling a DEM with counting the DEM pixels, which are between starting elevation and another elevation that gets incremented step by step. The second method is called the DEM contours method, and it consists in intersecting the DM with a set of water contours. The third method that will be compared to others is we call the profile contour method. And here, instead of using a continuous information of the bank's topography of the lake, we use discrete banks elevation profiles. And the final method is called we call it the height area method. And this is quite the most widely used method. It consists in matching water surface areas with direct water surface height measurements from radar altimetry. Just to go a little bit deeper in each method, for the DEM method, we used 1 meter resolution Pleiades digital surface models. This is an important point. They are digital surface models, actually, processed with the MICMAC photogrammetry software and derived from pairs of stereo images ordered at the end of the dry season when the lakes are as dry as possible. The residual water surface on the DSM are masked, and they are used to compute the starting elevations. And between each elevation of the process, we empirically set an increment of 10 centimeters. And this method will be represented by blue dots. Yeah. The second method, the DEM contours method, here we intersect the DSM with a set of water contours which are derived from Sentinel-2 images, and through ad hoc MNDWI thresholding, which proved to be more efficient in our cases, more efficient than automatic methods with respect to the spatial temporal spectral signature variability of the studied lakes. And this method will be represented by orange triangles. And so basically for each water contours, their elevation is computed as the median value of all intersected pixels after an outliers removal based on the median absolute deviation criterion. For the profile contour methods, we use 2 different multi-beam LiDAR datasets. The first one is ISA2 LTL8 terrain data with an along track resolution of 100 meters and is represented by the green diamonds. And the second dataset is GDI L2A terrain data at 60 meters resolution, represented by the red stars. And so for each water contour, we compute the crossover points with the LiDAR profiles, and the elevation of the crossover points are linearly interpolated. And then, as the previous method, the water contour elevation is computed as the median value of all the crossover points elevations. And so at the end, we end up with 2 different height area relationships. And for the height area method, so we used Sentinel-3 radar altimetry data at a long track resolution of 300 meters and processed with the OCOG retracking. And we processed to the matching with the water surface areas from Sentinel-2 within a temporal tolerance of 3 days based on the results of De Fleury et al. 2022. And we also applied some thresholds on the Sentinel-3 data, such as a threshold on sigma naught and also on the waveform pickiness to avoid the multipix waveforms. And this method will be represented as by magenta crosses. Talking about the study area, so it's located in central Sahel, extending over Mali, Niger, and Burkina Faso. Over there, the rainfall is mainly driven by the tropical monsoon systems, with wet season stretching from June to October, and a dry season stretching from within the rest of the year, and which is really suited for optical imagery observations of the water bodies because there is a very, very low cloudiness. And so the rainfall has a latitudinal pattern ranging from 200 millimeters a year to 1,000 millimeters a year from north to south. Talking about the studied lakes, so we selected 10 reservoirs and 6 natural lakes. Their mean water surface area is ranging from 0.22 kilometers square to 21 kilometers square, and they are mostly shallow with depths mostly below 5 meters deep. And as you can see, they have varied optical water types, such as open water, moderate to high turbidity, temporary or permanent aquatic vegetation. Concerning the data that we used for the remote sensing data, so as I said, we use Pleiades digital surface models together with ESA-2 and JEDI data, and we had access to this data over the 16 lakes. We had access to Sentinel-3 radar geometry data over 10 of these 16 lakes, and regarding the in-situ data, they cover 8 lakes. They are of different types and they come from different sources. So we have, for example, real-time water levels time series from pressure transducers over 2 lakes. We have historical water level time series from gauge measurements over 1 lake. And we also have hypsometric curves, so either volume height or volume height area relationships that come from water management agency or from existing studies. And these over 5 lakes. Going on with the results. So here, as you can see on the left panel, we superimposed the high relationships of each method over each lake covered by in-situ data. First thing to know is that there are elevation offsets between the different data sets. So for example, we don't have absolute elevation reference for most in-situ data and for most Pleiades DSMs. And in addition, we have different elevation references between the other remote sensing data. So we basically resolved these offsets by taking as reference the DSM Pleiades contour dataset, because it provides long and regular clouds of points. And so as we can see, we have a generally good agreement between each method. We are very glad to see that we can retrieve small height amplitudes ranging from 1.5 meter to 5 meter, with most amplitudes below 3 meters. And it's very interesting because many existing studies either focus on deeper lakes or they use 1 meter vertical resolution digital elevation models such as SRTM data. We also observe a generally good agreement of all methods with in-situ data, which are represented by the black crosses, except for 2 reservoirs, but where all remote sensing methods still remain consistent. And in terms of accuracy, we have an RMSE, we have most RMSE values below 30 centimeters. Just to show other results or the observations. So here is over 2 lakes that are not covered by in-situ data. And we are glad to see that the different methods consistently observe fine shape patterns, such as slope breaks. And these slope breaks makes the curves look more like degree 3 polynomials than degree 1 or degree 2. And it's interesting because many existing studies fit their height area relationship with degree 1 polynomial. Here I give some cautions with the different data. So with the Pleiades DSMs, we observed when comparing with the Copernicus DEM GLOW 30, along track undulations of several meters, and it's concerning lakes covered by Pleiades 1B satellites, especially. And so these undulations are caused by the jitter of the satellite between the two image shots. And yeah, this suggests that preliminary checks have to be done before naively using the Pleiades data. And it has been quite largely documented and also on other satellites, not in Pleiades. In our case, we corrected this we corrected it by subtracting the average per line with the difference with the Copernicus DM. Another caution, here you can see a zoom of the Pleiades DSM over a particular area of the North Tenvi reservoir. So as you can see, we have a noise on the lake bottom of the reservoir caused by low pixels correlations due to this very smooth area, and the peaks and the troughs caused by this noise force us to underestimate the starting elevation of the process in order to take into account those pixels in order not to underestimate the water area for the rest of the processing. And so this is what caused this hockey stick pattern. Another question on the GDI data we observed. So here you can see height area relationships derived from GDI data from different acquisition dates. And between those acquisition dates, we observed quite important elevation offsets that can reach up to 50 centimeters. And yeah, as the data quantity allowed it, here we simply we selected the most complete and the least noisy acquisition date to derive the resulting height area relationship. Other pieces of caution, here is another example. Two things, as we can clearly see the dependency of the curve extents to acquisition dates for the LiDAR and DSM derived methods. So the LiDAR methods are the red stars and the green diamonds. And so as you can see, the height area relationships are derived from these methods do not go as deep as the other methods because the LiDAR overpassed the lake at the high water level. And we also can see that we often observe higher noise on the Sentinel-3 derived curves, which we attribute to either waveform contamination by surrounding bright surfaces or to lakeside. We also try to assess the water elevation precision of these methods, and especially the methods using either water contours or, let's say, water surface areas from Sentinel-2. And to assess how flat these methods observe the water surface. And so for each method, we computed the median absolute deviation of the elevation along the contours or along the transects, and we stacked those median absolute deviations in boxes, and we split them among the different methods. And so we are glad to see that if we consider the median absolute deviation, we have good results with most precision values below 20 centimeters for Pleiades, below 13 centimeters for ESA-2 and GDI, and below 6 centimeters for Sentinel-3. And we have also good precision stability with interquartile ranges below 20 centimeters for all methods. Next slides of the results. So here we switch from height area relationships to volume area relationships. So this is the left panel, and on the right panel we show the normalized root mean square error that we have compared to the in-situ data. So just to go quickly, it's not easy to give a winner between the different methods, but the different methods perform not similarly from one lake to another, but we do not observe systematic differences between the methods. And for our methods, we have NRMSE values below 20% and MOS values below 10%. To conclude, we computed the height area relationships from 4 different methods, and we compared them over 16 lakes in West Africa. We use different sources of data, such as digital surface models, optical imagery, LiDAR, and radar altimetry. We have a generally good agreement between the methods and also with respect to the institute data. We have consistent observations of fine shape patterns over small height amplitudes, and we can retrieve the water elevation with satisfying precision with all methods. We also identify some inherent limitations of each method with respect, for example, to data quality, surface features, temporal coverage, etc. What we did not discuss, but also have to be discussed, is the spatial coverage of the different data sets and the data accessibility. And for the outlook, we try to combine the open source data, so Sentinel-3, GDI, and ISA2 derive height error relationships. And we saw, as you can see on the lower right figure, that it allows providing more robust relationships and improves the curve's extent. And this can be particularly interesting for engaged lakes or lakes with outdated in situ data. And so all these results will be published in a paper that is currently in preparation. And thank you for your attention.
Thank you, Felix. Do you have questions for Felix? So I have one. If you have to choose one method, which one you take?
It's the big deal. I'm not sure we really have to choose only one method, and it really depends on the extent of the study. I mean, for example, the radar altimetry derived method is really limited by the spatial coverage of the radar altimetry. So can be combined with the LiDAR altimetry derived method. So, and yeah, we saw that, for example, the LiDAR altimetry derived method is really performing well, and it can challenge the high resolution digital surface model derived method. So it could be a really good method to use, but it has also its own limitations, such as the acquisition dates dependency. So in my opinion, we should better use a combination of the methods when it's possible.
Okay, and how do you see the upscaling of this method? Because now you focus on 6 + 7 lakes on your area, but I see a potential to do this at the scale of the entire Sahel or Africa. We're talking during the discussion, even like in Ecuador. So do you see a potential for this?
Yeah, I see a great potential. So actually, the rest of my PhD will focus on SWOT. So to upscale the height error relationship computation, we are planning to use SWOT data. But in my opinion, maybe LiDAR data could also do the job. But we have to be aware of these temporal limitations.
And just before I give to Santiago, just one. Did you look at SWOT data already on your area? Did you have the opportunity or no?
Just started.
Okay.
It's the beginning.
Okay.
Nice. Yeah. Hi, Felix. Nice work and presentation. 2 questions. First, about vegetation problems. Did you have like some particular methods for particular lakes just to say, okay, we know this is water, we put it, we correct that like in a particular way, or?
You mean for vegetation on impact on which data?
On the water extent.
The water extent. No, we used fixed MNDWI threshold, and so we tried to also to minimize the error with the other methods such as OTSU or minimum error thresholding method, just to be sure that we are computing something that is realistic. But no, we didn't use other things with respect to the vegetation.
Okay. And second question, you had one lake that had like a different or divergent bathymetric low. Is that because maybe the in situ data were like from a different period or something? Maybe you can show.
Yeah, it's also one of the questions we have. So for I mean, we have two reservoirs where the performances are not as good as for the other. And yeah, here the institute data are quite old, but it's an ongoing work. For now, we don't have real conclusions.
Thanks.
Okay, if we don't have any more questions, we can move to the next. Okay. Yeah, go ahead.
Hello. Well, thanks for the presentation. I was just wondering about the uncertainty in the water extent, because I don't know how flat these lakes were, but for example, in the mountains, the elevation could be changing very abruptly, and 10 meters in uncertainty of the water extent, for example, in width, could be a lot of uncertainty in the water height. So how are you handling this, or are you providing some kind of uncertainty for the different methods? Because I guess that each method has their own thing going on.
Yeah, it's so maybe I can go back to this slide. So here, actually, the water elevation precision that we try to assess for methods that are using water contours, these assessments also include the water contour precision, the water contour detection. It's a mixture of contour precision and elevation precision. So this can be one assessment of the water area uncertainty. Sorry. Also, you mentioned lakes in mountain areas. Here we have mostly shallow lakes, so the impact of water surface area uncertainty is maybe lower on the water surface elevation.
Okay, thank you. So now we move to the last presenter, Nick Everard, who will talk about global stream flow analysis.
Okay, so we're back to rivers. I have a prop. You can have a think about what my prop might relate to, but don't shout it out. We'll come to that later on if I remember. I put my phone here because I always overrun, so I'm going to try not to overrun. Okay, anyway, so I'm Nick Everard. I'm talking about the FluviSat project. Stands for Fluvial Video Satellite. And essentially, we're trying to measure stream flow and specifically water velocity using video and still imagery from satellite. So moving on, I added this slide this morning. For those of you who were here yesterday, you'll know that I talked a little bit about potential of new space. So I thought I'd rechristen myself New Space Nick, as it's a bit of my theme. But moving on, I mean, we talked about all this stuff several times yesterday. So there's nothing more critical on this planet than water. So we're trying to quantify its presence and availability in rivers. Some of the problems, flooding. This is a flood in Bozkurt, Turkey. Sadly, it killed over 90 people. But when you think about trying to measure a flood like this with traditional methods, it's very, very difficult, very, very dangerous. This was a very rapid flood. So we had a little discussion yesterday afternoon about whether or not there's potential for measuring these kind of floods with satellite Earth observation. We can talk about that in breaks. Water resources, equally critical. Just to illustrate the point, I've put out, what's the pointer on this thing? There we go. Yeah, this is Lake Mead and Las Vegas in the US. Here it is, here's Las Vegas in 1984. Here it is in 2016. I'm sorry, I couldn't find a more recent picture. The population has gone from 500,000 to 2.4 million. Meanwhile, Lake Mead has gone from a reasonable amount of water to much less water. So you can see growing population, decreasing water resource availability. Another problem, monitoring networks. There's been discussion of monitoring networks being in decline. In some cases, the monitoring networks are just destroyed by the flood. This is a big flood that hit the UK 2015. This is the remains of a flow gauging station that was situated here. And just to give you some perspective, the river is normally in this section here between that building and the hedge line. None of this is normally river. So trying to measure this, trying to quantify this with traditional methods is very, very difficult. Here's another one, enormous morphological change. this hut was about to fall into the river, and a few days later, they got rid of it. So yeah, monitoring networks can be actually destroyed by the floods themselves. And of course, climate change is going to make everything worse and everything harder. So what's our concept? What we're trying to achieve is a direct measurement of water speed. So, we've talked about methods of trying to determine water flow speed, but they are all, to my knowledge, they're all indirect methods. We're trying to do it directly and not only give you one value of water speed. These are some actual readings which we've derived from our analysis. We've got 21 readings of water speed across the river. And the fact that we've got 21 gives us confidence in the results in themselves because we see a logical distribution of velocity across the river. So we're quite excited about this. So what's the principle of this? So basically this builds upon a technique that's been developed probably 20 years or more ago, but more recently it's been popularized and made much more effective through the availability of low-cost drones. So basically, you shoot video, you hover your drone over the river, you shoot video looking straight down at the water surface. You can take an oblique view if you want to, but the geometric distortion is more significant. But if you look straight down at the water surface, and then you're just quantifying the movement of visible features. If you can see, let me see if I can make that play again. We go back and then go forward again. Yeah, so you can see the movement of these features on the water surface. So if we can shoot a video, we can analyze, as long as we can scale it, and we've got the presence of those features, we can make a pretty accurate analysis of water surface speed. And the vectors you see here were generated from this video. So the thinking was, if this works using a drone, why can't we put the camera a bit higher? So actually, I have to give a shout out to Mark Randall, who's part of our project here. Mark Randall is a hydrologist working in Queensland, Australia, who about 6 years ago told me that he had become aware of Planet's capability, Planet Labs, a commercial provider, their ability to shoot video from space. And once I got back up off the floor, we talked about this and we were like, well, this should work. There's no reason why this wouldn't work. So yeah, we're taking the same principle we use with the drones, but just putting the camera a little bit higher up in space. So the Planet constellation, the SkySat constellation, the SkySat is their most high resolution satellite. There's 21 of them. They can shoot HD video, better than HD video. It's 2560 by 1080 at 30 frames a second. And they can achieve multiple daily revisits. So one of the benefits of using this constellation is we can actually revisit the same site up to 7 times a day. The images you see here are for a site in the UK where there was a small amount of cloud cover, so they reshot 4 times in 24 hours. So, an incredible capability in terms of resolution, in terms of the fact they can do video, but in terms of revisit times as well. So you probably want to see a video. Here is a video. So this is the Indus River in Pakistan. If you look at these features here, you can see them moving. So as soon as we got our first video, we were pretty confident this was going to work. We can see the movement, so can the computer algorithm we're going to use to analyze it. So we obtained you can see that it wanders as well. So, the targeting is pretty good. But, anyone who's ever used a camera with a zoom lens or a phone when you zoom in, it's hard to keep it fully stable. So we'll play that again if I can make it. Here we go. So yeah, it wanders. It also changes slightly in scale because the satellite is moving at, I calculated 27,000 kilometers an hour. But its displacement in space is about 225 kilometers from when it starts capturing the video to when it finishes. So its position relative to the area of interest changes. So the geometry of this changes. So quite a challenge was to stabilize this, first of all, and then rectify it. But you can see the raw materials are there. We can see the surface features, by which I mean these kind of roughness features, and we can see them moving. So, just to clarify from the outset, if your river doesn't have these big surface features or has static features like standing waves that you can't see moving, it's not likely to work with the current technology. So validation. So for the first phase of this project, we had a 12-month project, and then a 6-month extension on that. So during the first phase, we really tried to get out there and collect validation data. So this was our validation technique. We would capture the satellite video and endeavor to synchronize that with capture of drone videos and with measurements with ADCPs. These are acoustic sensors mounted on boats, in this case, a remote control boat. And they produce this fantastic cross-section They also give us a velocity profile. So from this data, we can analyze this data and understand the relationship between the surface velocity and the velocity deeper down into the water column. So we can apply a multiplier to the surface velocity because you can't calculate discharge just based upon surface velocity. So that was our kind of validation method. So just as a really nice example of how well this method worked, we were able to obtain 6 videos. Planet got 6 videos for us of the Pakistan floods of 2022 in the space of 2 weeks. And within the frame of each video, so the frame is about 2.5 kilometers by 1 kilometer, we were able to do velocimetry in multiple places. So again, we couldn't get out there to do validation at this site, unfortunately. But what we can do is kind of self-validate. We can see the logical distribution of water velocity vectors across the river, and we can see how it changes as we come into this straighter section here, how it migrates across and hugs the bank over here. So we can kind of self-validate. And the fact we were able to obtain multiple video collections at this site, it also enables us to track rises and falls in discharge. And we subsequently got more videos of that location this year. Here's another example. There's been discussions of ice on northern rivers. We realized that when the ice was going to break up on the Yukon River, the ice makes the most fantastic tracer. So I said we need surface roughness, we need foam, whatever. Chunks of ice are just perfect. So we waited. It was a sort of a game of guessing, really, when it was going to break up. But there is a fantastic resource. Anyone interested in ice-covered rivers may have already discovered Fresh Eyes on Ice. Have a look at it. They publish daily photographs of the Yukon and other rivers that are prone to freezing. So I could see, I think it's going to break up. And we got this fantastic result. So we chose a location where Environment Canada have a gauging station. So their gauging station is about here. So I was confident, I knew I had a time series of water level, had a time series of discharge, but I also contacted them and said, hey, do you have any ADCP gaugings? So of course they didn't have one that was synchronized with when I was there, but I was able to take the cross section from this and adjust it for the change in water surface height. And I could get the velocity profile from this. And this is the actual data they gave me. So how well does it work? In this particular example, we calculated, well, we've got 2 values. The gauging station was giving us 8,520 QMEX. We calculated 9,400 and 8,800. Why the difference? I don't know if there's any hydrometrists in the room, but this is calculating using the method that's popular in the UK, the mean section method, and this is using the mid-section method. So it's just a subtle difference in how you calculate discharge when you have panels in which you're calculating discharge. But you can see the scale of difference between the 2 calculation methods is way bigger than the difference between, say, the better of them and the discharge from the gauging station. So we're very happy with this. We don't really know, because I've never worked on frozen rivers before. We've looked at this velocity profile. We don't really know what the velocity profile is once the ice starts to form, if it changes. It may do. Of course, there was a catastrophic destruction of a dam in Ukraine earlier this year. As soon as I saw this on the news, I requested an acquisition. One of the problems or limitations of this method became apparent. We requested it immediately. Planet put it on their tasking immediately, but it was a week before we had a clear view of the Kakovka Dam. But this is velocimetry of the flow coming through the dam. We calculated discharge based upon the best we could get hold of was reports of the height of the dam and a guesstimate of the size of the breach. But we also informed this with some reporting from reservoir dam specialists. We calculated about 9,500 cubic meters per second at that point in time. So that's using video, but we were also looking to see whether we could use still frame imagery for velocimetry. So still frame imagery, this is from the SkySats as well. This is how it looks. The SkySats have 3 cameras arrayed kind of like this. So one camera is sort of looking ahead of the other 2. But it shoots at 50 frames a second. And we said the video is 30 frames a second. So what's the difference? The difference is it doesn't lock onto the target. So we get a 0.3 of a second exposure of our area of interest. So the question is, and here I'm going to hop between slides as quick as I can, several times. Can we see movement in 0.3 seconds? And I don't know if you can see that up on the screen or not, but we can. If the flow is fast enough and the features are big enough, we can see movement, we can quantify it, we can map it. So this is 1 kilometer of the Zambezi River. And this is velocimetry that represents this fast flowing section here through these rapids and the slower flow down here. We've also got direction as well as magnitude in this particular analysis. So yeah, we're pretty blown away with that. And yeah, to mention this data came through an ESA-ERSRIN allowance. So we were able to get a lot of data at no cost through the ESA-ERSRIN program. Sorry, I hate it when the slide changes when you're about to take a picture. There you go. This is where we got our acquisitions all around the world. I'm probably running out of time, so I'll whiz through this. Here are some of the benefits. It allows flow measurements on large-ish rivers. The narrowest where we got good results was the Zambezi at 50 meters wide. So when we say large, you know, it's all relative. Anywhere in the world, no people or equipment are needed on site. So particularly in flooding, it can be hazardous and costly. Multiple daily revisits. I can't overstate the value of that in dealing with, you know, events like flooding. Validation and real-time training of global hydrological models, it's got great potential for. And finally, I've worked in hydrometry, the measurement part of hydrology, for a long time. And it's always been kind of, you know, the low-profile part. There's very few people. I'm the first person to use the word hydrometry this week, I think. It's really cool. What we're doing is really cool. People get excited about it. I get excited about it, you can tell. Problems and issues, obviously cloud cover. Optimizing the imagery, the exposure of the imagery, as well as the stabilization and rectification. Getting ground-based info, we want to validate, but we can't always get ground-based info for validation. Workflows, we need a slicker workflow. You know, what we've got works well. This morning, in response to the discussions on the South Sudan earlier this week, in fact, yesterday, we're proposing to get a video from South Sudan. It's very unlikely we'll have it processed by Friday, even if we acquire it before then, because the workflow isn't that slick. So we want to make it slicker. Money, it costs money to get this data, but I think we should expect to get it because our work is important enough. Illumination makes a big difference. From one video of the Indus River, this is the first frame, this is 15 seconds in, and this is 30 seconds in. So understanding the angle of the azimuth, I think you call it, of the satellite relative to the water surface, makes a big difference. It makes no difference to the land surface, but to the water surface, it makes a huge difference. So we want to try and understand that better. Opportunities, we can't measure the surface height very well at the moment, so altimetry can help us. Here's a picture of a car park. Why do we have a picture of a car park? Here's where I screwed up. This is where my prop comes in. I was going to say, let me go back. What's this? It's a bag from Pret, right? It's a pixel. It's a pixel. So this is Pleiad Neo. This is 30 centimeter pixel sizes. They've now gone to 15 centimeters. And this week I saw Umbra publish a SAR image with 16 centimeters. That's the longer side of my bag. The shorter side of my bag is 15 centimeters. So that's a pixel nowadays. That's my point. The car park, this is Glastonbury Festival. It's a huge festival. It's like a town that appears in Somerset every year. This little piece here is what you're seeing here. So that's at 30 centimeters. And we can almost identify the make and model of cars in that imagery. So what we can do for hydrology is really exciting. Outlook, I added my Outlook slides. Yeah, hidden in the back there, new space. I think there's big potential there. Water is only going to get more important as a risk and as a resource as climate change impacts scenes, growing populations. Potential for wholly remotely sensed river monitoring is close. You know, we think by combining this method with others, we can get discharge readings without any in situ data. Huge potential for data sparse areas. I think Africa is perhaps the continent where there's the greatest potential. What we have achieved is really just the start here, I think. Recommendations, dedicated missions, re-optimizing existing missions. We need to be bold. Hydrology, water is really important. So, you know, I was really excited. Airbus acquired some imagery for me. They fiddled with the settings on PNEO to try and optimize it for what I wanted. That was really nice. iSight captured a SAR video for me for free because I asked them to. And it was astonishing. What we can do with that video, we don't even know yet. But, you know, we should expect, because what we're doing is important, hybrid missions are needed, or hybrid solutions rather, combining optical, radar, whatever else. Effective partnerships are needed. We want to break down if there is a barrier between research and commercial sector. You know, we want to break that down. Yeah, and synergies between platforms, satellites and drones. So much of what we can do with a satellite, we can do with the drones. So much of the metadata and so on that we need is common to both. I haven't really got time to talk about this stuff. But I think my final slide, I think, is this one. I put this in some time ago. I think it's the most exciting advance in hydrology in my lifetime. You know, I might be biased, I don't know, but I think it's pretty cool and exciting. But then I added this one this morning. Today is impossible is tomorrow's routine. I don't know if that's a fresh quote. I dreamt it up instead of having breakfast this morning. But my point is, you know, to the discussions, the kind of discussions we were having yesterday, what might seem impossible right now, it's probably going to be easy pretty soon when you think about the advance in pixel sizes and stuff. And my final thing, various people have advertised sessions. I'm going to advertise a session. I'm running a big session, a union session at EGU next year on advances in measurements. So we'll cover EO, but we want to cover all sorts of other topics as well. And I've probably way overrun and eaten up my question time. So that's it.
So we have time for 1 to 2 questions. Yeah, okay, there's many.
Well, thanks for the presentation. It was very interesting. I was wondering about 2 things. First, how do you select the features that you afterwards going to analyze? And secondly, I think I like the picture there. I think I kind of see waves due to the wind. How does wind play a role in your imagery? Because I guess that it adds features that you don't want to include in your analysis.
Yeah, it's a good question. And it comes down to site selection, and it also comes down to the software we use. So we're using, again, we're actually using, I mean, there's open source software can use, but we're using a commercial software called Hydrospace. It stands for Hydro Space-Time Imaging Velocimetry. And it's very good actually at kind of identifying those kind of features and removing them. So they developed it for use with drones and bridge mounted cameras and everything else, but you have the same issues. So site selection is really important as well. So I spent a lot of time looking on Google Earth for places where I think this is going to work well. And we've had some places where it hasn't worked well, but overall, I think where we've been able to get a comparison discharge, I think we've always been within 10%. But you're right, site selection is really important. I think when we choose sites like, you know, this kind of site, this is just perfect. I think the water is sufficiently energetic and the features are big enough that we don't really see a wind impact. So I think if we were able to start, I mean, you know, if you had lower flows, slower flows, smoother surfaces, then you might start to see the impact of wind, but we haven't seen it as a significant factor so far.
Thank you.
Okay, now the next question.
Yeah, very interesting presentation. I was going to ask a question about monitoring ice flows, but you're covering it. But the other aspect of Arctic rivers is ice jams and flooding resulting from the ice jams. So I think there's also great potential.
Well, I think about
more of a comment.
2 days after we got our video, there was a big ice jam flood on the Yukon, which I normally have the slides, but I had to cut them out.
Yeah, there's also.
But there's also the ice pancakes. We just got a video a week ago of the ice pancakes on the Yukon. So as it starts to freeze up, for several weeks, you get these fabulous sort of pizzas of ice that float down the river, and they just make perfect traces.
Yeah, and there's something called javes. I'm not sure if you read about this. Javes are ice. You get ice jams, and then there's the blocking, and the water behind makes such that you get these huge waves coming down the river. So it's been documented in some rivers in northern Canada. So great applications, of course, in Alaska, Canada, of course.
I think the 2 areas where I'm most excited about furthering this research is Africa and probably these northern rivers as well.
Yes, thank you for your presentation. It's very impressive. So we knew we can see swimming pools, and now we can see how people are swimming fast or not. My question is, okay, so you have the velocity at the surface. But then to know the discharge, you need to know the cross-section.
Yeah.
So it means you need in situ ADCP measurement sometimes, I guess. For every location you want to compute the discharge. And then you also need to have the elevation, I guess.
Yeah.
So if you need a local ADCP and if you need elevation, so by satellite, so then how better your discharge is compared to a classical rating curve that you could design.
Well, I think as I kind of hinted at towards the end, I think if we can combine multiple sources of information, I think it's going to be possible to do it without needing anything on site. So I think we do need the cross section. And I think for some rivers, you know, where the river goes pretty much dry or very low, we can develop a kind of DEM from in the, when it's dry. But I think, for taking the Indus, I mean, this is one of my favorite sites, but, if we could get out there and get some cross sections, they would be so valuable. And I think, some rivers are subject to significant morphological change, but in a lot of places, if you get a cross section, it's not going to change much over a number of years. So if you get it once, you've got it. And then part of the reason I show stuff like the car park, my vision, well, I started to have this, why don't we just have a gauge board we can read from space? An inclined gauge board, not a vertical one, but, a demarcated board on the, you wouldn't have to make it that big to read it with PNEO. So then you've got your water level, but we could get it from altimetry. But, I'm just really excited about the potential of very high resolution data. So, your question is a very valid one, but I think there are answers available to address that.
Okay, thanks for this nice presentation. Besides the ice tracking, which will be maybe the ideal case, something like big features moving, the rest of the cases you show is always linked to turbulence or turbulent water. And did you have some correlation on that or some studies on the water?
Not really. I look on Google Earth.
Be able to have like this water roughness.
Yeah, no, I mean, literally, I spent a lot of time on Google Earth. I'll Google rapids on certain rivers and whatever, but you usually don't want to use the rapid itself. So I don't know, do I have one of?
What comes after?
Yeah, because you need what works best generally is sort of downstream of the rapid where the flow and the roughness features kind of detach themselves. I don't know. Oh, here's one. So yeah, it was kind of, it's not that clear in this one, is it? But you don't want to be doing it here because there's a lot of static features. You can see the water flowing over these rocks, causing these, that's not moving. But once the flow starts, the roughness features start to detach and affect with the flow, that's where you want to work. So if that kind of answers the question. But yeah, we don't have any sort of sophisticated sciencey way of doing it. It's just eyeballs and Google Earth.
Hi, just a curiosity. Did you face some problem with the sun glint, and how did you handle it?
Yeah, not really. I suppose the answer is, I think we could do, but in fact, what we saw, I think when we're closest to getting what you might call sun glint, we actually got really strong signal. So I think we potentially could, it could kind of bleach things out, but we didn't. But I think we really want to learn more about the acquisition angle, the azimuth, because with so many satellites, with 21 satellites, they claim they can image the same place up to 12 times a day. I think in reality, it's more commonly it's about 7 times a day. So whether we choose the 9:40 a.m. acquisition or the 10:15 acquisition, could make quite a difference, because if we get something that resembles this rather than this, we can get much better results. So we've got a lot of more research we want to do, and that's exactly one of the themes. And we did get another one. We got one on the Dnipro River downstream of the dam after it had been breached, and the water was just a completely flat grey surface because we didn't have favourable illumination. So I think understanding that illumination angle is going to be quite key.
And I worked a little bit with the SkySat data. Sometimes they have some misregistration problem. Did you have them, and how did you solve that in order to stabilize the?
Stabilization was quite difficult. Where's Guy? Guy and his crew kind of led on that. But somebody, I don't know if this is what you're referring to. The last speaker mentioned jitter, which is a new term to me. I'm fairly new to all this stuff. But I found it in the still frame imagery that I was working with. Where did I put that? I had this kind of like undulations in it. And, if I plotted and I switch, when I was showing you how I switch from one frame to another, like here, and we see the water surface move, but I would also see the land surface seem to ripple in sort of linear fashion, and no one's explained to me why that happened, but maybe that's jitter. Who was it? Where's Felix? Was it Felix? Did you talk about jitter? Is that jitter? If anybody knows about jitter, come and talk to me. But it's like the land surface was set onto corrugated iron, but would sort of move. Right. It was always very linear. It always seemed to be diagonal, but anyway.
Okay, So exciting to see so many questions. I just one more. Do you know if there's application for waves? Because it's very important to monitor the seashore, shoreline position. You know, it's the first application you see with movement of perpetual water. So do you know if they do that already?
Yeah, I mean, the first thing, so Mark Randall, whose idea this was from Australia, the very first video he got hold of, he just found it was published online. He analyzed it, and it was waves breaking on a beach, and he was able to measure the speed of it. But I think, you know, our big challenge is cloud cover, because, you know, floods are driven by rain, and rain comes out of clouds. So, you know, we have found that there's several days delay. So I think we want to cross-fertilize ideas, because I think, you know, I'm interested, can we get a Doppler shift from a radar signal that represents water speed? I think that kind of thing's probably been done in the kind of marine environment already, but whether it would work for rivers, we don't know, but we want to find out.
Okay, thank you. So we have short time for the seed questions. Anyway, our session is the last of 3 already session where we had seed question about techniques of remote sensing. So so with Fernando, we imagine some seed question that could be the continuity of what we had yesterday, but also exploring other perspectives. So we divided the seed questions into 2 parts. Ones are more related to science and one more to users and society. So I don't know if you see one you would like to discuss, because today we went also on the large spread of scales. So going from, as you see, like a video looking at below the second movement to Jean-François who showed us, or with Grace, like very long-term climatic data. So on the science type question, it was more like, what are the knowledge gaps and what do we want to tackle new with remote sensing? Then yesterday we talked with Jean-François Créteau, who was at the WCRP meeting, and he showed that there was a gap between what we are doing and the climate world, which are more still on the atmospheric part. So how can we engage these people? Especially we know that now we have more recurrent hydrological extreme, especially, for instance, in the Amazon now. So how can we engage the climate community to use our data on the surface? Because they are still using precipitation, but the hydrology from the surface is not used by the climate scientists. Then the last question that we had was more related to yesterday also, but it comes down to also the video. Do we have enough? Did we reduce enough the uncertainties to use the hydro data in the operational context? And what is the latency time that we need? Because you even with the video, you were talking about few days, but is it enough in the operational context? And then, okay, you can talk about the one from society.
Yeah, maybe just as a summary because we're almost now ready for the coffee break, but it was just to see, we've seen so many technologies. So the question is, do you think that maybe the use of such technologies, it's constrained by data availability and also knowledge on the methods to extract the data? And also nowadays, for all the proposals that we have to write in order to get funding, we have to include stakeholders at some point of our project. So where would you want to include stakeholders? Is it just from the beginning, or just at the end for communication? And finally, well, a little bit dealing with what we've seen also in this session and also yesterday, the funding of data. So especially now with commercial products like the one we just saw, like, is it really a constraint to improve the knowledge on water resources, especially in the global south? So I don't know, maybe all of you have experienced that that we know a product that we can use, but the problem is just the funding. So, but okay, I think we can maybe leave this as food for thought, and then maybe we can just like fill our stomachs now in the in the coffee break. Thanks.
Thank you to all the speakers.
Just present the person. Yeah. I mean, if and also for just the just the can start speaking. Yeah.
Shall we start?
We do? Okay. Okay, so good afternoon, everyone. Hope everyone had a good lunch. So we're going to have this session on the first session on the afternoon regarding precipitation, rainfall, snowfall, also some reference to floods. My name is Nuno Moreira. I'm chairing with my colleague, chair colleague Luca Ciabatta. And as you know, it's a 20-minute per session. We try to get, we give the 2 minutes at minute 16, so you know that you're still in time, but for time for questions. And so I would start already with Guy Schumann from ESA-ESRIN. Go ahead.
Thank you. Thanks for having me here. I mean, probably some of you are still digesting, so I try to keep it a bit entertaining and move a bit fast also that we have enough time for discussion or if you have any questions. So yeah, I'm from Hydrospace, but I'm a person with many hats. So I also have an affiliation with Bristol University, and I work also in my free time, which I don't have, but I work as a consultant to the UN, FAO and WFP for during flood events, especially helping them to understand when they get flood maps from left and right, literally what they should be doing and what they should be using, or to make their decision a bit easier and faster. So, and that led me to try to develop something that we could be saying, okay, maybe ML is the right way to go if you want to map globally floods, if you want to look at multi-sensor application, and if you want to map faster and also with consistent accuracy across different biomes on Earth. So I have started this process with ESA's support in InCubed. So InCubed is a program with ESA where companies can get support, but they also need to contribute some funding to it themselves. And then you can develop ideas around Earth observation. So that's really great. And it allowed me to start this development that I want to go into. Also, of course, eventually also make some money with it. But above all, for me, it's very important that it can also be used by humanitarian services. And who may be paying or not paying, that's not the important question. The important question is that it's also useful not only to the UN, but the Red Cross and Médecins Sans Frontières. And they all have different needs and different sectors have different needs. So that was also a challenge. But here, a little bit of outline. I'm going to go into an introduction, which I don't think any of you need to hear again, but it's very obvious. But I'm going to switch straight away to some very cool flood scenes from Sentinel-2, optical around the world. So to show you that it is quite tricky to map floods from optical. And then actually what is flood sense application and the ML model behind it, and then assessing performance skills, and then also where we are running flood sense right now or where we plan to run it. And then where are we now, you know, and then a cool project we actually started. Thank you. Okay. Yeah. And then also a very cool project we started right now. We signed the contract this month with ESA. I'm very proud about this because it's a long journey for me to establish this project, and it's talking about trusted products in Earth observation. And then, of course, business partnership, but I can skip that since here is really a science workshop. But all of these things are quite important if you want to put some stuff from science into market. I try to remember where these floods are, but I could also ask you that question, but we don't have enough time. So all these images I show you are images that show a river in flood conditions, whether it's a flood condition in the river or whether it's some overtopping. But here we are a stretch of the Niger River, just to show you again how complicated it can be, because there's a lot of green stuff or greenish stuff on there. A lot of that green is not at all water, but some green is, and some green is not flooded, but then others is, and you know it's just quite difficult. So here's my favorite, and that's no contrast enhancement. I've done nothing with this image, just displayed RGB. This is Mozambique, just after a tropical cyclone, so the clouds have cleared, but you see the enormous amount of reddish sediments being transported. And that gives you yet another color in the flood. So if you imagine this, and you want to have normalized difference water index, thresholding the waters in both, it's hardly possible to set it at the same threshold. So here again, this is, I think all of you know, or probably have seen this. This is the Sentinel-2 cloud-free image of the Pakistan flood. It's also to show you, you get tons of cloud-free images actually during floods. So this is again, Pakistan, 2022, very unfortunate event. Killed a lot of people, killed far too many people. The response, I don't know, I'm not a response person, but I know that there is a lot of data that could have been received earlier, but wasn't landing to the right people. So that's another challenge. This one is absolutely beautiful. It's much better on this screen than on that. But I could ask you where the water is, but I think, I don't know, there's probably one person in the room, as she presented, is Beatrice. She knows where the water is. The water is literally everywhere, but not the flood. It's a wetland. So, and there's this famous refugee camp up north that looks like a checkerboard. So the flooding is right in there, the brownish between the white blocks. And then there's this strip of dry land, brownish reddish, and it's all very, very difficult. And again, imagine an NDWI band ratio traditional algorithm to map all of these biomes and give you a flat map. It's hardly possible. And there's also the problem here with the spatial resolution, of course. Spectrally, Sentinel-2 is very powerful. It's like Landsat 989. These are really powerful images, very well calibrated satellite instruments for retrieving this, but spatial resolution is sometimes not what we want it to be. Here's Spain, another beautiful image, but again, very different biome. Here is the one that made us think, well, it should be possible to retrieve something under the cloud, because this is Mozambique, a lot of cloud cover every time, but you also have these beautiful cloud-free patches that you can observe the flood. And then with some intelligent processing, topography, etc., it may be able to retrace that shoreline under the cloud, etc. So what would be the value proposition? Of course, disaster response, much better disaster response if you can map all of this with the same level of accuracy everywhere. And then also the insurance and reinsurance market could be interested to use this for insurances, especially parametric. But above all, we are also addressing a lot of these sustainable development goals if we can manage to do this correctly. So in InCube, it's very important that you show ESA, you're very serious pulling it to an end user. And so we had two end user sectors, the disaster response from the United Nations World Food Programme, and then reinsurance. We have very lucky to get Willis Research Network on this to tell us what the reinsurance sector would be interested in. So this was really to define gain, pains, and user requirements. And actually, it's funny because when I did that first, I didn't think that both sectors were so much alike in their requirements. The toughest one is the United Nations, because the insurance is okay just to have a well-trained model, for example, on an AOI they are interested in, whereas the UN tells you, we want the algorithm to perform well everywhere. And every time there's a flood, we want an image. So that's something we know we can't meet. We talked about this yesterday in the discussion. Getting every flood type every time is just not possible. So, so what is actually the flood sense application? It's what I like to call a living ML model. The machine learning community is moving extremely fast. If you think you're using the right UNet version of a model today, tomorrow is a different one, and there's a better one. So you need to construct an ML that's able to update with new functionalities and new machine learning models as they are built and tested. And then also keep the model multi-sensor. Now we're getting the question, okay, what about you putting in SAR at the same time as optical? And then we're also getting the question of hyperspectral and maybe thermal. So traditional band ratio, that just isn't possible. You would have to run multiple algorithms over multiple images, but if you have a good ML model well trained on all sensor types, you could imagine that eventually you could have it all in one box, and it wouldn't care which image it gets, it would just process the flood map using the right machine learning model for that flood. So that's what we want to do. And preparing the data, of course, this is a boring slide, but it's the most difficult task. You need to reproject the data, make them overlay extremely well, and then stack all the bands into a single raster, and then do these stupid ML little tiles. And then you get a problem at the edges because there the satellite or the transformation, maybe you have it slanted. And so there's a lot of these issues that nobody really wants to hear about, but that takes a lot of the time. When you have actually built the architecture and everything else, it's not so difficult. It trains very well. It does the job well. And if you use the right architecture, for example, we used an explanatory AI architecture. We use the squeeze and excitation network before we feeding it to UNet. So the network can also understand which input layer is important. And this is important for us because we gave it all the channels in Sentinel-2, plus topography, plus slope, plus topographic wetness index, plus a grid, a static grid of where we think water may be flowing across the topography. So all of these layers, and then the squeeze and excitation network can actually tell you which one of the layers it used most to infer the results it got. And then the other very nice part of a machine learning, if you let it display, it will display the result as a floating point number between 0 and 1. So immediately it gives you a confidence level of what the model thinks it should be, how much wet the pixel should be. So I think I can skip this, move a bit faster. So we have cloud-free cases at the beginning just to see if the network's working without big problems. So this is the image I showed you before. We got very good results on cloud-free images, very, very clear water features. Balaton is a permanent water example, and Sudan is water mixed with flooding. So decreases a little bit because of these color differences I showed, but it's still very, very reasonable. Here's interesting, sorry about the blurriness, but the red is not correct when comparing this to an OpenStreetMap, very high resolution water mask. And by the way, yes, when we tried to, as a reference data set, we also tried to pick Picel data, JSE. They are not very good if you want to show that the ML would be better than all these algorithms. You have to use something that you're quite sure came from a much higher spatial resolution source and was also vetted. And that's why we opted for permanent water for using the OpenStreetMap data. And as you can see, we can map very, very small features. Sometimes we get it wrong, but it's generally very good. Here again, rivers, but you see where we go very, very small channels, we don't map them, but that's a resolution problem. Again, here, very good performance we even get within urban areas where we struggle a bit picking up the water features, but we're doing quite well overall. So here, the end of that lake, I think, again, the same message here. So if we deal with clouds, how do we do it? So our first test was with permanent water surfaces. And then, of course, all these flow accumulation grids I just told you about and digital elevation model, we use Copernicus 30 meter because it's the one that's open access and free also for commercial, etc. So when we do that, what you get is actually, skip that as well. This is a typical, very annoying scene from Sentinel-2. It can happen a lot of times, even without a flood. You get these scenes and you just want to know where the water is, where the river is running, and you can't see it. So that's a true color image. That's the permanent water labels from OpenStreetMap. And that's the flood sense inferred results. And we were amazed that it could actually find the running rivers across the cloud on the upper right. You see it very well also on the lake parts. But here it's more obvious. It's running the river right through the cloud. Here it's amazing. Again, the ones it misses are the very small channels. So we asked the squeeze and excitation network what input channel it used. Of course, it can't tell us it used Sentinel-2 because it's not visible. It's just a cloud cover. So it said it just ran with the slope of the DEM because it's a zero slope. The technology of the DEM can't see where there's rivers, so it gives you a zero slope. So it was just using that to run the river. But it's nice because we never told it that this was a river on the DEM. So it correlated the heights correctly or the slope correctly, the slope values, it correlated them where it could see the river, and then continued that line through. So in a way, you could claim it was trying to learn something, although I don't like that part. It sounds a bit scary when you say it like that. But it was actually doing some height inferences from slopes. It was then looking at, so I see the river where there's zero slope, so I continue that zero slope feature, but I don't see anything on the Sentinel-2. And so results are quite good. Clouded, we get again to say it's 90%. We are not losing much compared to before, but that was a permanent water feature, which is very easy in a DEM to spot. Now, if we go into floods, we still haven't cracked that nut. It's very difficult to do flood mapping on a floodplain where there's hardly any slope at all, but there's a little bit of slope, so the DEM has no zero values, but it keeps on giving you a slope. It's very difficult for the ML to understand how to map floods below that cloud cover. But we have some initial results on following the shoreline heights. Anyway, so here we did the Pakistan model just to show you a bit more validation. It's quite good. We tested two approaches, so having a local built machine learning model versus a global transferable model. And I show you some nice results there. So if you test it on the Pakistan South image and you trained on that region or similar regions, you would always score very high, which is like basically testing the robustness again. But if you then trained on another landscape area, you do very poorly. If you just do on one and then you infer again on the Pakistan South where we have the validation, it decreases by almost half, right? So you do very, very badly. But if you then put around the world similar biomes in the training data set of floods,
2 minutes,
you can really increase it very, very rapidly again to a reasonable number. And this is the global transferable model. So this last row is the global transferable model. And I think we've also shown that you can move in that direction. So we run it for now on the WASD cloud. It's available, but we actually build it so that it can also, now we're running it also on the Google Cloud. So it can be run on any platform, or we feed the results from the MPI. So this is the last slide. And this is the project we are starting now, is to take our flood maps and the ML algorithm and run it through a data tracing and workflow tracing certification process, so that in the end, anybody can be sure that we really used Sentinel data. We didn't use a generative AI to produce the flood image, believe it or not, but that's very much possible today. And we can tell the customer, the user like the UN, where the other data sets came from, and that is really using these data sets we say. And then we also give a certification that the flood map is using a machine learning algorithm that was not inferred by any third party. And this is actually the biggest selling point in commercial of this product now. People don't want the flood map, they want the trusted map in this era we find ourselves in. So that's the project we're starting right now with ESA. So here's a nice video, just if you want, just take a photo for the link. It's a really nice video where we also pull all this into visualization. So to tell people what it really means to have a flood map. It's difficult to explain as a raster map, but if you show it in a 3D visualization with impact on real buildings where people live, is much more powerful. So again, here's the last slide and the outlook and recommendations. I think transferability is hard but feasible, and clouds are mostly an unsurmountable problem, but it's possible to do. If we take a hybrid model, it's possible to do if we include more dynamic water flow algorithms, for example, from a model. We need data and this authenticity and this traceability that I just talked about a little bit. And then, of course, all this goes into this famous AI Act that's about to come out from the Commission. And then about, how do we blend in this precision of the satellite data, the intelligence of the AI and the maturity of technology and all these cloud platforms that are out there? Where can people get this data? What are the expectations? That's also crucial. So anyway, I hope I've given you a bit of an inside look of what we're doing, but thank you very much.
Okay, thank you. We have still 2 minutes. So a question, time for a question. It's lunchtime, you know. Okay, you still have time in the end. So we have some minutes for discussion afterwards. So if you have any questions, you can then pick on that. So we now move to the next presenter. So Noah, Molort from the University of Colorado.
Great. It's nice to be here, and thank you for the introduction. I'm going to talk today about some work we've been doing to map snow water equivalent in mountain ranges around the world with a focus on the Sierra Nevada mountains of California. And what I want to do, it actually dovetails well with the previous talk, is focus on the adaptive capacity that's been developed through mapping snowpack to inform water resource management. And so the case study that I'll focus on is from this past winter, which was pending some analysis of the data, perhaps the record snowpack year for the Sierra Nevada mountains. And the legacy of satellite measurements that we'll leverage here in the presentation date back to the EOS era for NASA and the Terra and Aqua spacecraft and the MODIS instruments. And so one of the things that I want to convey in this talk is the degree to which we can make incremental improvements with satellites that weren't necessarily designed to measure the variable that we're interested in this case, snow water equivalent, but we can build capacity with these incremental measurements for the water resource management community to become accustomed to working with the data that we're going to provide from future satellite missions. And so within the remote sensing community globally, there's an effort aimed at developing a snow dedicated mission. But for the water resource management community to be in position to utilize data from that mission, we need to develop data products that they can start using and becoming comfortable with. And importantly, that they be trusted, which was something that was emphasized in the previous talk. And I really like the concept of thinking about trusted data. And so the point I'll make with regard to snow is that because water resource management in semi-arid mountainous regions around the world is so heavily focused on snow, there's a potential for adaptive capacity when it comes to the remote sensing of snow that may not exist for many other water-related variables. Now, to bring some emphasis to this, there was some analysis done in a paper published by Immerzeel et al. In 2020 in Nature that brought attention to where snow and ice represent particularly important water sources around the world. And we can see in Central Asia, in parts of Europe and Scandinavia, in parts of Western and North America and South America, there's a particular focus on snow and ice as an importance for a water source. And in that paper, we see that the places where snow and ice are a dominant portion of runoff, they're also in very high demand. And so I would make the argument that, again, this makes snow perhaps a great example for adaptive capacity in that there's a very strong interest in data to quantify snow. And as a result, there have been many fits and starts in the snow remote sensing community to develop satellite missions. The closest that I think we've come was an ESA mission proposal of Core H2O, which did not move forward. But my mentor and one of the prominent snow hydrologists in remote sensing, Jeff Dozier, termed remote sensing of snow water equivalent the holy grail of snow hydrology. And I think that's the reason why we've got this incredible focus on trying to develop the technology to measure snow from space. And yet we have a number of hindrances to develop that technology. And this is a relatively busy graph, but this articulates the different snow remote sensing estimation techniques in the second column from left here. And the color in the snow-related variables listed across the top, the color shading represents the technological readiness level. So green indicates that the technology that's indicated here is relatively adept at measuring the variable of interest. And if we focus our attention on the fourth column from left, snow water equivalent, we can see that the techniques that have relatively high technological readiness level for measuring snow water equivalent have issues that limit their applications in wet snow. So if there's any liquid water present within the snowpack, they have limitations with regard to forest cover, limitations with regard to complex terrain. And so all of these kind of make this a measurement challenge where we have limited capability for remote sensing of snow water equivalent. And so the objective for the work that we've been doing is to overcome, excuse me, some of these measurement technologies, these measurement challenges by developing a snow water equivalent data fusion system that brings together ground measurements, remotely sensed measurements of snow, in particular snow-covered area, and distributed models that represent the distribution of snow. And so this SWE reanalysis approach is something that we were supported by the NASA Applied Sciences program to develop back in 2008. And through collaboration with the water resources management community, we've been delivering operational snow data in real time throughout mountain regions across the United States since 2012. And slowly over time, the water resource management community has increasingly come to the table to utilize these data and provide us feedback on how those data are useful. And that led us up to this most recent year of 2023, which I'll show some imagery on in a moment, which was one of the biggest snow years on record and was therefore a year with very high demand for snowpack information. So the way that we're approaching our estimation of snow water equivalent is schematically indicated with this cartoon that shows the data sources, with the benefits from satellite data being the relatively large spatial extent, high temporal frequency, the continuity in the data, and efficiency in the data collection. But of course, we're not able to measure snow water equivalent. We're able to measure other snow-related variables like snow cover extent. Doesn't get us to where we really want to be. Ground sensors have the benefit that we can directly measure snow water equivalent. They have high accuracy and high frequency, as well as continuity and a long legacy of ground measurements across the Western United States dating back to the first half of the 20th century. And then more recently, we have a system called the Airborne Snow Observatories, which was developed at NASA JPL and is now a private company run by Tom Painter and his colleagues. And that is now a $10 million a year program in the state of California that provides operational LiDAR measurements of snow depth across the Sierra Nevada. So we bring that data source into the snow fusion system as well. The snow fusion system is a statistical modeling approach that relates the operational ground measurements to spatially explicit data, including topography. And so the network is shown in the map on the right. There are over 800 snow sensors across the Western United States. In the focus area of the Sierra Nevada, there's about 120 of them. And if you relate the measured snow water equivalent in real time collected in this network to measures of the topography with all the various variables that one can derive from a digital elevation model shown on the horizontal axis, what you'll see when you compare the R-squared values that there's not much statistical power. You're not explaining a lot of the variability in snow water equivalent with any single topographic variable. The median R-squareds are listed from left to right in the order of rank, with the highest R-squareds on the right-hand side of the graph. And I want to bring your attention to this bar on the this box plot on the far right, which represents the R-squared relating the snow water equivalent on these snow pillows to a satellite-based historical reanalysis of snow water equivalent across the mountain range. And that box plot here indicates that historical information regarding snow water equivalent derived from models and satellite observations of snow-covered area have more statistical relationship with snow water equivalent than any topographic variable. And so we should be exploiting that historical data as much as possible for estimating snow water equivalent in real time. If I had more time in this talk, I could explain what was behind those reanalyses, but I'll defer you to the literature in that regard. So this is the statistical modeling approach that we use for fusing all these data sources together. The dependent variable is shown across the top, where the point measurements represent those over 800 snow monitoring stations across the Western United States. We scale those with a real-time observation of fractional snow-covered area from satellite so that they better represent the grid cells at 500-meter resolution that they lie within. And that gives us our dependent variable in the linear regression model. The independent variables represent all of those topographic metrics that I showed on the previous slide, the details of which are really not that important. The important part is this data cube, which represents daily historical snow water equivalent from 1985 to 2016 across the mountainous area, in this case for the Sierra Nevada. And we can statistically sample from this data cube, which represents thousands of daily representations of snow water equivalent, to identify which historical sweep pattern shows the highest correlation with the dependent variable. And then also we combine in a daily mean fractional snow covered area up to the day of year of interest so that there's a time series of snow covered area, which effectively is how white a pixel is through time relates to how much SWE resides within the pixel. So the argument that I make here with this SWE data fusion system for the water resource management community is that this isn't going to give us the most accurate estimate of SWE that we can possibly derive, but it's going to give us a product that is continuous in space and in time, and one that can begin the process of integrating the data into water resource management. And it provides a system whereby we can integrate new observations into the fusion system as they become available, either by new satellite observations of snow depth or snow water equivalent that could be brought in as a dependent variable in the analysis, or as spatial estimates that have some correlation with snow water equivalent that could be used as a new independent variable to improve the SWE estimates. So getting down to the nitty gritty of the snow water equivalent distribution in water year 2023, which is this record year, large portions of the state just being completely buried in snow. States of emergency were in place. And there was a lot of concern about snowmelt runoff flooding in the spring, as well as a lot of concern for rain on snow flooding in the middle of winter. And I think the state of California really dodged a bullet in that we didn't have any warm atmospheric rivers come in to the state during this winter, which would have dropped rainfall on this very deep snowpack that we had. So we averted that rain on snow situation, which is good news from a water resources perspective. We preserved the snowpack and the high elevations, which gave us an abundance of water supply. The April 1 snow water equivalent is shown across the Sierra. Just orient you geographically. The San Francisco Bay is here. Lake Tahoe is right here, if that's meaningful. to a European audience, I'm not sure. Los Angeles would be just down off the bottom of the map here. The percent of averages are shown by pixel. This is something that the Water Resource Management community really likes to focus on, is what are the percent of averages in addition to the actual volumes of water that are stored. Also summarizing by watershed those percent of averages. So we're 225% of average, for example, in the Kern watershed, which is down here in the bottom, versus as you look toward the northern part of the Sierras, they're closer to about 150% of average. So that was the story for mid-February. And then as we moved into mid-March, you can see the dark blues getting darker, deeper snowpack across the Sierra, more dark greens here indicating percent of averages closer to that 300% mark. So 3 times the amount of snow that would normally exist on the ground at that time. And then percent of average by watershed shown here with, again, that Kern hitting over 300% of average. And across the south, many other watersheds also going above the 300% of average. And then the important date of April 1st, this is the date that the water management community uses to forecast the total spring and summer runoff. And by that time, you can see that the dark blues have really intensified across the Sierra Nevada. And I'll just note that this amount of water represents about 50 cubic kilometers of water across the Sierras, which if you drape that across the entire state of California, would be about 12 centimeters deep liquid water across the entire state. So a huge volume of water in a place that is in constant water demand.
2 minutes.
And then by May 1, we see the snow water equivalent. Now we're heading into the melt season, so the margins of the SWE are reducing. The percent of averages remain quite high. Now, in terms of adaptive capacity, I mean, I'm showing you some example maps. The way that this data is displayed has been done in co-production with the water resource management community. And one of the things that you start to see as you engage with the management community of natural resources is that it can be very hard to break through and get your data into their hands and to get them to utilize your data. But once you do break through, you've kind of started, pun intended, snowball process that you can't easily stop. And they will come to you and want the data with increased frequency over time. And it becomes your responsibility, in my opinion, to deliver that data. And as the community of people that are coming to you and asking for data grows, you find that your time spent on doing other things begins to get smaller and smaller. And the time spent that you dedicate to supporting this community becomes larger and larger. And that may be a personal thing for me, and that I find it particularly rewarding and extremely interesting to see the problems that the water management community are dealing with, which I think next to a career in research is probably one of the more exciting water-related professions. And so the real breakthrough came for us when we started to see that the water management community in California came together to develop their own data tools where they can bring together data sources from a number of different remote sensing products. Here's one of the example tools that I'm showing you here that the state of California developed. I'll bring your attention to this graph, which is for the Feather River Basin. And you can see different snow water equivalent products with the abbreviations that I won't go into detail on for the interest of time. But they basically have 5 different SWE estimations plotted through time that they can use to evaluate consistency, and then water supply volume forecasts that they base on these different data sets shown across the top. And this is just for one example watershed, the Feather River Basin, which flows into California's largest reservoir. So in summary, I've given you an example of how some of the technological challenges associated with snow has forced us into a place of innovation and data gymnastics using a number of data sources to try to get at snow water equivalent, which is kind of that holy grail variable. That can lead to a lot of capacity building with the water resource management community that will be critical to have in place once we actually have that snow satellite mission. And I think with regard to other water measurement platforms that exist within the portfolio in orbit, this can provide an example of how one can approach the problem of building capacity and having the community ready when satellites are put into orbit. And with that, I'll take questions.
Okay. Time for a quick question, a quick answer. I don't see any. Oh, yeah, there is one.
I'm not sure it's a quick question, but anyway. Couple. First of all, thank you for your fantastic job you are doing with local stakeholders. I can confirm it's true. Two questions. The first one, you said that you were using past SWE as one of the predictors. And I was wondering about the correlation about that past SWE and the current conditions in 2023, an unparalleled year in terms of total amount. Did you see some decrease in correlation or some less reliability of previous SWE as a predictor? And the second one, more science to some extent. I saw that if I look at the positive anomaly of SWE across the Sierra Nevada, it was higher the more south you go. We know that the Sierra Nevada increases in elevation the more south you go. I was wondering what was the process driving that besides mere elevation?
Yeah, thanks for those questions. So one of the things that, from a statistical standpoint, the Sierra Nevada have very few years that are near the mean. And the archive of 20 years in terms of those past patterns and correlating them with the current condition in a big snow year is actually benefited by the fact that there are many large snow years in that 20-year archive. So I don't know that we would see a drop off in the statistical power in a bigger snow year. We do, as climate changes, predict that the past will increasingly be less representative of the present. So I think that's underlying your question as well. The second part of your question, remind me, was related to the path of the atmospheric rivers that we had in the Sierra Nevada this past particular winter favored the southern Sierra Nevada. And that's why all the ground data and our analysis support the conclusion that the anomalies were much higher in the south.
Okay, thank you. And let's move to the third presentation by Nuno Moreira from IPMA.
Okay, hello again, now from this side. So I am Nuno Moreira, as mentioned. I come from the Portuguese Met Service, so I'm a meteorologist. And I would like to also to mention the authors of this work, which are also from IPMA and EMETSAT, and some acknowledgements that we want to mention here for the work that I'm going to present. It's about two recent cases of daily precipitation, very extreme events that happened in Madeira. So we're now coming back to the Atlantic, and I will talk to you about these two cases. So the beginning, how this started. There was an event of heavy and persistent precipitation very locally in Madeira. Madeira we are here, right? And it's 1,000 kilometers to the southwest, here in the middle of the Atlantic. This is the island, the main island. And there was an event here in this area on Christmas Day 3 years ago. And the problem is that we had high impact due to landslides and mud and debris flow. And these were some of the impacts that are very clear. And in fact, within 1 month, there was 1.9 million euros of interventions due to this event. So Madeira is really a hotspot. We have been checking other places in the Mediterranean with problems, but here we really have a problem with heavy precipitation events. So in the middle, what happened? This event was in fact underwarned on our case from the warning perspective. It was the first event that happened after that we start having a radar there and the lightning network. And because of this, we had an extensive report that we produced focusing on the quantitative estimation of precipitation. But the report also included weather analysis, the other observations, numerical outputs, climatological context, and soil moisture analysis. So what happened after? So half a year ago, we had another event. It was on the 5th and 6th of June. The 24-hour precipitation amounts ranged between 300 and 600 millimeters happening in the mountain. So, but in fact, as you know, and you have been talking about these days, it's this spring and summer, we had many situations already referred here in the Mediterranean. So, of course, I'm talking now about the Atlantic, but these hundreds of millimeters of daily precipitation are currently our day-to-day almost problem and concern. So what did we use and what will I show to you? I will show to you, of course, the automatic weather stations from our IPMA, our network. I will show you also the dual position radar from IPMA network that's located in the island of Porto Santo, which is to the northeast of Madeira. And from satellite, I will be showing the SAF nowcasting product, the convective rainfall rate product with 1 hour accumulation and then up to 24 hours. And also from Hydrospace, the accumulated precipitation at the ground by blended microwave and infrared, both the H05, which was discontinued, and the H61. And we'll be focusing on 24-hour accumulations, basically on 024 UTC on the first episode and 12 to 12 on the second one. So this was the first case on 3 years ago, the Christmas day. We can see here already the maximum values, and I have to tell you that the yellow starts at 125 millimeters per day. So we had this maximum value of 223 in Porto Muniz. This was, in fact, the fifth highest amount of 24-hour precipitation in Madeira since 2000, but it was the highest in a coastal area, so not in the mountain here in the middle. So the others were in the mountain, and this was, in fact, the highest in a low-level location. Also, we had a hint that there was another maxima here with lower accumulated values from the automatic weather stations in this range, 75 to 100 millimeters for 24 hours. And of course, we went to check the radar, and the radar was something completely different somehow. So we could see here a band of precipitation with more than double of the amounts that the automatic weather stations was giving to us. So you can see one maxima here, both over the ocean and over land. Over land, we had this maxima of around 500 millimeters in 24 hours. This was using the Marshall-Palmer ZR relation from radar, and after the removal of the hail effect. It was found in this report that we did that this, in fact, resulted from the anchoring of convection to the orography. So it's a phenomenon that happened under an eastern flow. The levels of instability were moderate, and the level of total precipitable water was also moderate, so not very high values here. But the problem was really the persistence of the convection on the same place due to this anchoring of convection, which is this scheme here to the right. So this is the same image. Now, just mentioning here, just for you to check the Marshall-Palmer experiment, which depends on drop size distribution. Later, we did another estimate with the radar, which is using the ZDR method, which regards a dual polymerization parameter that is linked to cloud microphysics. And in fact, this amount here is slightly lower, so more on the 350s, let's say. But anyway, it's a big number because it's over land. So if you want to, we compared, of course, for some locations. Here you can check that the surface observations are in red, and the ZDR method from radar is the green triangle, which is closer, especially in these high values. So in general, the ZDR-derived rainfall amounts from radar are closer to the ground truth, let's call it, compared to the Marshall-Palmer. So then we checked the satellite. So we checked these two products from the SAF nowcasting. We checked the convective rainfall rate accumulation, which confirmed clearly the higher values over the ocean. And here are the values over land and over the ocean. And we also checked the HSAF H05 at the time, which was putting the maximum values to the north with lower values here over land, suggesting the parallax effect. So that's why over land it was just 31 and then 160 over the ocean. But in fact, not all the in fact, we know that all the products have problems. And for the SAF nowcasting, there was clearly, if you see hour by hour, you see this is here in blue, you have the automatic weather station in Porto Muniz, that one that reached the more than 200 millimeters. And in orange, you have the SAF nowcasting estimate. So there was clear, and another estimation during the night, which is already known, but it was very, very clear here. And there was also not only an overestimation, the slope is different, but there was also a phase lag here. And this phase lag is basically related to the heterogeneous precipitation within a pixel that is large enough to be over land and over ocean. So there was a big lag. So also the SAF nowcasting, although it had a total amount that was similar to what we were having in radar, in fact, if you go on a continuous step-by-step way, there's no agreement, no full agreement. So this is basically, I think, what I had to tell you about the first case. Then the second case, what I will show you here, it's the 14 to 14 first, 14 UTC, because these were the higher amounts. We had in these stations, all these stations here in Madeira, we had these accumulations that were ranging from 350 to a value of 600. Of course, we had some suspicions on this number, but we are still having it to show. But you can see that these 5 stations, they are all in the mountain areas, are with very high values. In fact, 2/3 of the stations had more than 100 millimeters in 24 hours. So this value here, this peak of 600 millimeters, was measured in this weather station. You see the differences here to the other weather stations, but all in mountain areas. This event was a persistent stratiform event, stratiform precipitation, so different from the other case. There was a nimbostratus cloud in a very moist environment. There was strong orographic precipitation enhancement, as you can see. And also there was some cirriform clouds in the upper levels, which I will talk about in the next slide. So this is now the plot from the weather stations, now from 12 to 12. So the value is now some 50 millimeters lower. So only 550, more or less, in this 12 to 12. If you see the radar, the 2 estimates from the radar, the Marshall-Palmer on the left, the ZDR on the right, which we had better results on the other case, you can see very clearly that you have this beam occultation to the southwest of the island. So the radar is here in Porto Santo Island, and you see it's very clear from this side and on the border. But here to the south of the island and over the central part of the island, we have an occultation of the beam, so clearly a depletion here on these values. Also, you had some spurious clutter here in the center, which is due to windmills. Some are removed, some are not, but the central part is very difficult also because of the windmills. And we could find that the ZDR, if you compare directly to the stations, was also better than the Marshall-Palmer estimate in terms of radar. Then we looked at the SAF nowcasting CRR product, the 24 hours. You could see clear that there is high amounts to the northwest of the island, like you have it here. So in general, it looks more closer. But then you have spurious values here on the south coast. You have also a night underestimation, day overestimation, but you have this spurious accumulation, which is related to the cirriform clouds that I mentioned that were detected and gave these spurious values that we could analyze. And finally, with the H61 from SAF, you had here the lowest accumulations of all these estimates, so a strong underestimation. One thing is that if someone was entering the room right now and would look at this, maybe they think they were different cases because they are really providing different estimates or different looks of what's really happening. So that's a big issue that we still have to deal in operations in terms of nowcasting, namely. So I think I'm now in the conclusion, hope in time. So I will show here the pros and cons for each source of accumulated precipitation for these two deriving from these two extreme cases. So the automatic weather stations, they are accurate, of course, to determine the precipitation amounts. They have also problems, but they should be accurate enough in the place where they are. But they have a sparse spatial distribution and may miss local maxima, as it happened very clearly in the first case, and which, of course, happens in convective events. The radar, of course, they have an aerial coverage with, in this case, the ZDR method outperforming the Marshall-Palmer ZR relation. We noticed that the accumulated precipitation values are in the same order of magnitude, so they are not exactly, we are not calculating bias and root mean square errors here, we're just looking at the order of magnitude. But there is clearly a problem with the beam occultation to the southwest of Madeira Island, and there is also these windmills spurious values. Then for SAF nowcasting, of course, there is a complete aerial coverage, but you have the problem of underestimating during the night and overestimating during the day, and of course also these spurious pixels. And from HSAF, also a complete aerial coverage, but also, again, as I mentioned, the strong underestimation of the total amounts. So you see, but in all of this, and this is why it's so important. So we have clearly a hotspot in the middle of the Atlantic for precipitation, and we have all these issues from each of the sources. So outlook and recommendations. Of course, what we want to do next, we want to go also to check some other products, starting with the convective rainfall rate from cloud physical properties from SAF nowcasting, EUMETSAT SAF nowcasting. Also check the GPMI merge, lower resolution, but we will have to do to check this. What we propose also into operations, nevertheless, is to integrate into our nowcasting activities something that I'm calling a multi-source blended loop up to 24 hours with 1 hour incremental accumulation. So this is starting at 0 and incremental gradually. And you see the two estimates of the radar in here and one from well, just an example. And you see here during the night, it's not accumulating. And then only during the day, it starts to accumulate. So these kind of things may be useful for our operational forecasters at the bench. And of course, follow the developments for next products, for next missions. I include here one of I know it's more in front of us, like the Meteosat third generation, which is already there, and products are going to be available soon with the increase of spatial, temporal, and radiometric resolution. But also for the sounder, the second satellite from MTG, also there will be this information on the vertical profile. And I leave also for the discussion, how about the next generations of low Earth orbit satellites to help improving this. And I think this was my last slide. Thank you.
Thank you, Nuno. Are there any questions for Nuno? Yes, please.
Thank you. Very interesting. Did you have any chance to look at H60 and on the SAF, because of things that
which is H60? I didn't.
H60 is a blend, also including microwave radiometer. You looked at.
This is H61 includes microwave.
Okay.
Yes, it's infrared and microwave. H61 we did, yes.
Okay, good to know, because I'm using H60, but
okay,
maybe it's a bit different, but not sure. Okay, we should discuss with it.
Okay, we can check.
Okay, thanks.
Okay, thank you.
Any other question? If not, thank you, Bruno. We can move to the next presentation by Bruno Picard from Fluctus.
Thank you very much. Actually, an excellent transition to my presentation because I will also talk about the atmosphere. So there's a lot of people here interested in rivers and lakes, but we will keep on the upper side of the planet. So I'm Bruno Picard. I will present you the very first results of a project called Rain GNSS. And it's a collaboration between Fluctus, which is me, and all the people at Vortex, Jean-Christophe and Yannick and so on. So quick overview, I will present context and the objectives, the characteristics of the GNSS receiver processing, the Earth observation and in-situ validation facilities of Fluctus, some very first results of the retrieval and the validation of water vapor from a GNSS station, and the perspectives for precipitation retrieval. So what is all about? It's all about having in-situ measurements of water vapor and rain, which are highly spatially and temporally variable component. And if you are not convinced after what you presented about rain, it's very difficult because it can rain at you know, in your street, and it will not rain in a street like 500 meter far. And so it's difficult. So MWP models, it's very difficult to have accurate precipitation, but it's also true for water vapor. In the same time, if you're using a radar for having the level of your river, of your lake, so the radar is going through the troposphere and it has a certain delay, which comes as an error of the level of your target. So if you want to achieve a centimeter level accuracy for hydrology, you would need a strong and accurate source for water vapor. And obviously, an accurate rain estimation is required for small basin flood forecast. As a matter of illustration, you have here the radar delay that is varying over this month of October at Albi in southwest of France. And you can see that this delay is varying between 5 centimeter up to 20 centimeter. And if you are using a model instead of a more precise measurements of this, so you can commit errors of more than 10 centimeters. So we are talking about a network, and about network, there is this network deployed by Vortex. It consists of a network of stations that is dedicated dedicated to real-time monitoring on a notification system for the river, the level of rivers. So it's a network of a new generation of in-situ remote sensors, but also an online consultation and alert services. So this is their latest station that includes a leader for the level monitoring, a wide-angle infrared cam for day and night measurements of the flow rate. And also, and this is what we're interested in, a B-frequency 3 constellation GNSS receiver and antenna that is used for precise point positioning. And this is very interesting because once you have this GNSS station, you are capable of retrieving the water vapor content. And it's something that is done on a national network for years with certain success. And the goal here, so you can see this is not so nice in the illustration that the GNSS signal is actually delayed by the water vapor content. It could be very interesting to have this delay also for validation of Earth observation satellite. So the goal of having this Rain GNSS project is to have a low-cost but robust hardware and the processing that could provide both water vapor and precipitation forecasting. This is example of application of those two variables. So on the top right, you have an illustration of SWOT observations over a river. So if you have, again, observation by radar, you would need dry and wet delays to correct for the impact of the atmosphere. And on the lower part of this scheme, so you have an indication of a gradients of integrated precipitable water, which has been also computed from a network of GNSS station. And the situation for precipitation is not ideal because the GNSS receiver signal is not exactly what you would expect to measure rain. But still, there is there is more and more paper about how we could forecast and measure rain rate from this GNSS station. And obviously, adding precipitation forecasting and retrieval to the vortex network would definitely increase the relevance and completeness of the vortex solution for flood forecasting and monitoring. And this is our motivation here. So this is a development step for this project. So Vortex has gone through an hardware selection and optimization. Then the precise point processing himself, and then the parameterization of the zonal total delay, which is the amount of delay due to the water vapor, mainly. And then we are going through the retrieval and validation on the water vapor monitoring. So this is where we are currently digging. And for the future, there will be the retrieval and validation of the precipitation forecasting and retrieval. A quick word on the characteristics of the GNSS receiver. So it has been designed to be autonomous in terms of energy and connectivity, but also to be deployed at large scale. So it means that it must be cost effective if we want to have a dense network. So Vortex is using an OEM precise GNSS receiver. And the raw data are processed by the open source software RTK Lab in the most up-to-date version. So concerning this precise point location, it works pretty well. You can see here the deviation to the altitude all along the month of October. And you can see that somehow the millimeter level localization is achieved. So it was the first steps. So we think we are in a good way to achieve our final goal. So how will we validate the water vapor computed from this GNSS station? And in the future, how will we validate rain? So we must have on the very same location, both the GNSS station and the validation of measurement. So this is why at Fluctus we developed this Earth observation and in situ validation facilities, which is my home actually. So on the left part, you have the so-called dependence, a very cozy guest house. And on the top, on the rooftop, we placed the Vortex GNSS station and the antenna. And on the right part of the house, we have a Davis weather station. So what you can see here is the solar panel. And here, some of you may see the GNSS antenna. And here is on the side of the salon, the Davis weather station with measurements of pressure, temperature, humidity, and rain rate every minute. So we are here now. We are at the retrieval and the validation of water vapor. Or say some equations to show you that it's serious stuff. But mainly is to say that the total zonal, the zenith total delay that is measured at the station is the sum of an hydrostatic component driven by pressure and temperature, and a wet component driven by water vapor. And on the GNSS station, it is also a calibre that is used to compute the total delay using the well-known Sastamoinen dry component formulation and retrieving the wet part as an unknown parameter. And there is a lot of parameters to tune, and we are here for the moment. We are turning buttons to achieve the most accurate retrieval of the water vapor. To validate this water vapor the delay computed from the GNSS station, we will use ERA5 hourly reanalysis to compute the two components. So the hydrostatic part is computed from surface pressure and 2-meter temperature that you can download from ERA5. And for the wet component, we used 2-meter temperature and the precipitable water vapor, or the total content water vapor. And this is what we will want to achieve in the future, okay? We are not here yet. This is the IGN, so the French national GNSS network. And there is a station at Albi. Albi is 40 kilometers from Rabastens. You see my house at Rabastens. And this is here the difference between the total delay computed by the GNSS station and the one computed from ERA5. So you can see that it is possible to achieve 1 centimeter accuracy, both in terms of bias and standard deviation. We have about 1 centimeter error in biases and 1.4 centimeter in standard deviation comparing the GNSS station to the ERA5. And most of the error is actually inside the ERA5 analysis due to interpolation both spatially and temporally. And where we are here, not so good. So maybe some of you saw the presentation by François Boy. He said, we are here yet when he monitored this pool. And we are not here yet, but we are confident in the fact that we will reduce that. So what we could see here is a total delay by the station in orange and by ERA5 in blue. So we are still digging for 17 centimeter bias between the station and ERA5, but for saying the truth, 2 weeks ago we were at 40 centimeters, so we are digging in the right direction, I would say. There is a bias, but if you correct for this bias, you can see here the zonal total delay computed from ERA5 in blue, from the Davis station in green. Both of them are very consistent, and the total delay computed from the station in orange. And it seems that we are also missing a bit of dynamic here. But as I said, we are very confident to achieve that in the coming weeks. And when we will be confident in our water vapor project, then we will dig for what happens in terms of precipitation monitoring. And this is the purpose of many papers trying to demonstrate that forecasting of rain and potential rain amplitude retrieval is possible. I will show you 2 quick examples of that. The one by this paper, you have the rain events here, yeah, rain events here for different days, and kind of filtering of the total delay that show you that this precipitation are coincident with a disturbance of the zonal total delay, sometimes before the precipitation event. So it could be used as a forecasting, but also probably used for precipitation retrieval himself. And a second paper compared different sources of past paper and comparing true detected rain and false forecasted rate for different approaches. And this very last feature studies show very nice detection rate with this method. So we will apply those two methods in our station to try to retrieve for rain also. So in conclusion, we try to develop to deploy a low-cost and robust scalable network dedicated to water vapor and precipitation for Earth observation validation, but also to have a complete view of the hydrological basin using vortex river level monitoring and completed it with precipitation. As a recommendation, we are strongly in favor of dense networks of in situ measurements, would it be GNSS station or other, to have low-cost, robust, and easy-to-deploy stations that would benefit to prediction of natural hazards, including heavy storms and floods. And I think that Earth observation missions dedicated to hydrology or atmosphere monitoring also needs a dense in situ network. I was a bit long, but thank you very much. That's it.
Okay, any questions? Yes, please.
Thank you for your presentation. I have a question. We have the rain gauges for the precipitation measurement, which
sorry, can you start again?
Yes, we have the rain gauges,
yeah,
which is a most trusted measurement for precipitation. And also, but the density is not high. And also, we have the satellite precipitation with the highest spatial and temporal resolution. But I was wondering, what is the advantage of using the GNS gauge?
What is
the advantage of your devices compared to rain gauges or compared to satellite product?
You can actually you can get the precipitation from anywhere because all the data are transmitted to a central station. So you don't need to be there to have the monitoring. It's low cost and easy to maintain compared to rain gauges. And I would not say that we don't need anything but that. Just it's a complementary information and easy to deploy and easy to monitor. This is my point. When then compared to a satellite, so precipitations overland is difficult. Also, it's very large scales we are talking about for rain precipitation at minimum a kilometer, but sometimes it could be 10 kilometer or 20 kilometer. Here we have a precise point. It's a usual issue of having very fine measurements of in situ and compare that to satellite, but it's a well-known problem. And we are talking here of the common problem of validating satellite with in situ measurements. So I didn't say that this is an ideal situation. It's something to be to complement other systems.
Any other comments? If not, thank you
very much.
Thank you, Bruno. And let's move to the last presentation of this session by Thomas Nagler.
Thank you. In my presentation, I will introduce you satellite observations of physical snow parameters in mountain regions in support of water management. And you see the co-authors from this work primarily from Envio, a company in Innsbruck, and the work is carried out within the AlpSnow project, I have to say. What is the objectives of this project? We are dealing here with the development of new algorithms for monitoring physical snow parameters. And this is done from optical satellite data as well as from SAR data, dedicated especially for high resolution, which is needed in mountain terrains. And this will support also the assimilation into snowpack models and hydrological models for science applications, but also for operational applications. Oops. In this presentation, I will focus a little bit more in detail on 3 physical snow parameters. This is the areal extent, then snow melt area, extent and wetness, and snow water equivalent. As we heard today, this is a quite important parameter for monitoring the water resources. And for algorithm development, this was done in the Alpine regions for 5 different test areas in different environments at different elevations, also north and south of the main ridge in the Alps, in order to cover different meteorological situations. And each of these test areas was equipped with detailed in situ measurements from ground measurements, but also airborne measurements or terrestrial scanning, like laser scanning and so on. And this was very useful information in order to validate the different Earth observation-based satellite data and products. I will start now with the snow extent, which is a traditional parameter. Actually, as you see here in this image from Sentinel-3, acquired in March 19, that snow can be very well detected if you look for the reflectance in the visible band and in the shortwave infrared band at about 1.6 micrometers. And based on this spectral information, we can very easily formulate a quantity called the normalized difference snow index, which uses this information in order to detect snow. This was actually a very successful measure in order to use it. It was developed already years ago and applied to various sensors. And when we look to this in mountain terrains on a higher resolution, we see that this is a Sentinel-2 image acquired in November over the Swiss Alps. And we see very strongly the shaded regions caused by the low solar incidence angle. And when we follow the profile of the NDSI along this profile from northwest to southeast, we see that the NDSI is going towards higher values when we are reaching the shaded regions, although there is obviously no snow present. And applying traditional algorithms like Salomonsen and Appel for this region, we immediately detect snow in these dark regions. And even if there is no snow available. On the other hand, the algorithm works very nicely, of course, when we are going to the illuminated parts on the southern slopes. Applying this, for example, these algorithms, we see that it's an excellent snow detector on the regions or slopes which are facing towards the sun. But on the shaded region, it obviously fails. It's also an excellent detector for the shades. We designed a new algorithm, actually, which makes use of all the spectral bands available, not only focusing on 2, but using all what is available on the modern sensors like Sentinel-2, Landsat 9, but also SLSTR and OLGI. Up to 21 bands can be used, and all this information are then used in order to estimate the fractional snow extent. The technique what we are applying is a kind of multispectral unmixing, and the end members for this are selected directly from the scene using a kind of pre-classification using various measures directly from the spectrum. In order to reduce the errors, we are also applying a combinations of the nearby end members in order to estimate the query pixel. And of course, what we can also do with this method is to apply an error propagation model from the beginning of the reflectance towards the estimated snow cover fraction. Now, in order to, just for one example, This method was applied to this image, and we see that it's more or less very correct on the shaded regions as well as on the illuminated regions. This method has also an advantage that we can apply it to the coarser resolution sensors, because the high resolution sensors in alpine terrain or in general provide every couple of days an overflight. Taking clouds into account, then the overall information on the snowpack is only a few every couple of days. And for the dynamics to reflect or to monitor the evolution of the snowpack in these highly dynamic regions, we see that daily snow information would be useful, and therefore we are combining medium resolution sensors and high resolution sensors together. And of course, to use both in a kind of snowpack model, we need a kind of agreement between both sensors. This is now a Sentinel-2, a Sentinel-3 image with SLSTR with 1 kilometer resolution, acquired over the Eastern Alps in April 2020. And based on this information, we can apply the method what I've shown before on this scene. We see the 1 kilometer gives already quite a good introduction where the snow is and where it fails. By the way, light bluish colors are 1% of snow up to this dark purple, which is 100% of snow. So the quantification is in percent. Now, when we are combining SLSTR and OLG, providing 250-meter products, we see much more detail, which is needed for the complex terrain. And adding on top of this, the Sentinel-2 with 20 meters, we see how complex the snow structure is, especially on the ridges itself. They're becoming snow-free, which is obvious and known in alpine terrain. And looking to this information, then of course, we have both high resolution every couple of days, but on a daily basis, also the coarser resolution reflecting the snow dynamics. We intercompare it when we are aggregating the high resolution to the coarser resolution pixels, and we see that they are almost consistent. So we are calculating here the root mean square error and the bias between the various products, and seeing that the bias between the 20 meters resolution of Sentinel-2 and Landsat 8 to the 1 kilometer resolutions of Sentinel-3 and VIRS and MODIS is in the order of 1 to 2%, and the root mean square difference is up to 10% in this range of order, which is definitely quite good. Now, looking to the SAR data, what can we do with SAR in order to get more information on the snow properties? And this shows you, first I will look to the backscatter signatures, and we see here one time series of backscatter in these bluish colors from Sentinel-1, starting in 17 with the 6 days sampling down to 2020, covering 3 winter periods. Together with the snow depth measured at the in situ station at the high alpine terrain, you see here on the left side the photograph of this region. It's a flat meadow actually at about 2,200 meters approximately. And we see that as long as the snow is dry, we have no or only a small impact on the backscatter itself. And the strong signal is achieved actually when the backscatter when the snow starts melting, then we see, of course, a very strong decrease of the VV as well as the VH, and also the ratio between both has some impact on this during the melting seasons. We also look in detail when the snow is dry, what we can retrieve out of this time series, but this is still under investigation. Now, a product what we can form here is a kind of wet snow melt product, and you see here an example from Sentinel-1 during the melting season in 2018. We start here in April, and in April, the very top where we have glaciers above 3,000 meters, which is shown in cyan colors in April and May. This is still dry zone, and this we are snow, and this we are getting actually from optical images. But of course, the dark bluish colors are reflecting the melting zone, the melting snow regions, and this is going up during the main melting season. The algorithm is based on the kind of change detection using both the VH and the VV backscatter. It was validated with a couple of different Sentinel-2 and Landsat snow maps using the algorithm before in order to look for the consistency of both products. And the overall agreement for a site in Ötztal actually is about above 0.9, which is quite well. And But just to be aware, the main differences what we observe in the SAR images is that we are lacking the classification along the snow line where we have patchy snow structure, because this cannot be detected by the SAR sensors. So here we have still some problems. So this is the main issue. Based on this one, we can also look a little bit more in detail to the different melt phases. And this is still a product in development. So we are, in principle, we have three different melt phases, which are characterized by the temporal change of the backscatter. So this is the early melt phase shown here in this bluish color. Then we have an intermediate increase of backscatter, which is reflecting melt and refreezing during this diurnal cycle. This cannot be observed actually by Sentinel-1 because we have a 6-day sampling, and we would need a different SAR sensor like a geostationary SAR or something like this, which is proposing or acquiring data during the day. Additionally, then at the end, we have the gradual increase of backscatter, which is characterized by rough snow surface and the broken snow cover along the snow line. Now looking for snow water equivalent retrieval, we heard about this already and the need for such a product, especially in mountainous terrain. And one of the approaches is to use SAR interferometry. SAR interferometry is an excellent technique in order to observe the accumulation of dry snow during the accumulation period. And we have to correct the interferometric phase for a couple of components, which can be well done using a digital elevation model, and also to use atmospheric information on the water content available. Then what we get is out this phase change of due to the accumulation of dry snow between two images. And this is directly related actually to the snow water equivalent when we are going to lower incidence angles, so which is shown at the last equation. So this is a very simple approach, but it's still a very accurate measurement. When you go for the right graph here, I calculated here for one phase cycle of 2 pi, the change of snow water equivalent for two densities, so for fresh snow with 150 and for a little bit older snow of 300 kilogram per cubic meter. And at L band, this corresponds for the fresh snow of about 80 centimeters accumulation, at C band at 20 centimeters. And for the older snow, it is about 40 centimeters and 10 centimeters. And I have to say, it's really a very nice method, which I like because it's independent on the structure of the snow and also on the layering of the snow. But there are still some challenges to be solved in order to get the operational product out of that. And one of these is that it works only for dry snow. So we need to combine it with the product I introduced before, which is using Sentinel-1, so C-band data in order to detect where the snow is melting. Then there is can be a kind of temporal signal decorrelation when we have very heavy snowfall, melt, refreeze, or a snow drift. And this might cause also gaps in the time series. We found out that L-band is much more robust than C-band. Therefore, everybody is waiting actually for NISA to be launched beginning of next year, or later on for Roselle coming in 28, 29, with 2 satellites flying information with Sentinel-1. Then we need also to look for a kind of reference points, so some points in the image in order to calibrate or to know how much accumulation is done for a certain amount of the phase change. And this might be still some workout, especially in remote areas. And there are SAR look angles in mountain areas, so very steep look angle in foreslopes or on very grazing incidence angle. These are still critical. Forested regions is still in discussion if we can get some information, but what we see, according to our current research, is that we have some masking effect of the forest, although coherence is in general preserved. And what we also need for this to apply these techniques is acquisition planning from the SAR sensors in order to get a continuous time series over the winter period. Currently, this was not happening using PALSA or SARCOM data, but according to the knowledge on the acquisition plan for NISA next year, it seems that a continuous acquisition plan is on the line. Now, this is one example, what we had a field campaign together, coincident with PALSA acquisitions in the Engadine regions on the Swiss-Austrian border. at about 1,600 meters and above. And there were a couple of automatic stations measuring the change of the amount of snow during this 2 weeks period. So shorter periods would be more suitable or better. But Balsa is just providing this, and we see very nicely that we have a kind of accumulation pattern which agrees quite well to the available in situ data, although they are quite sparse. And what we marked out here in gray are glaciated areas and also forested regions. But this is still a very promising technique, and we hope to get the right satellite data very soon. Now coming to the conclusions. So we have an improved set of algorithms for snow extent in mountain regions and other parameters using the full spectral capabilities of current optical sensors. There is still some issues that we have to be solved in this way, and this is, for example, to correct for masking of the forested regions to derive the snow on ground, which is in general needed for hydrological applications. And also a general problem for optical sensors is the snow cloud discrimination. And this is still an uncertainty or the major uncertainty in these products. Then we have a method for monitoring the wet snow in regions using C-band data, primarily Sentinel-1. And the main differences to the optical data is that it is along the snow line where we have patchy snow structure, but here we have some physical limits. And but it is consistent in principle with the fractional snow extent from the optical one. Then we have an experimental concept for monitoring the MELS phases, and this has been tested with Sentinel-1, but a more dense acquisition of the C-band data would be needed in order to track this melt-refreeze cycle during the day. And we hope that such a mission is soon be launched. Then for snow water equivalent, so the INSAR retrieval is a very promising approach. Some issues are still to be solved, but it's a physical-based method. We know the physics behind it, and we are actually waiting for the very soon upcoming SAR missions like ROSOL and NISAR. And all these products, what I have shown before, are actually already used in various scientific and operational hydrological or snowpack models, and they are evaluated, and the impact of these models on the model output from the snow and hydrological models is evaluated. Thank you.
Thank you. Thank you, Thomas. Are there any questions? So no questions. Okay, so I think that we can start the discussion part of the sessions. We have prepared some seed questions that just to start the discussion, but if you have any starting point, please go ahead. Don't be shy. The floor is yours. And if you want a new satellite underneath your Christmas tree, this is the right moment and the right spot to ask for it. So
maybe can I start?
Sure.
Luca, yeah, from here. No.
Yeah.
So what I would like to ask is, I put in my presentation the reference to the next, to Meteosat third generation, and it's clearly related to the fourth point there, I believe. So it's the increase of the resolutions, and we discussed this already in this morning, that if we want to go into higher resolutions, in spatial resolutions, we then also have to increase the temporal resolutions. We're going to increase in the regular Meteosat, so we are going to increase also the spectral resolution. Is this going to be enough for in case the precipitation estimates? Will this really enable us to solve these problems that we were addressing, and Bruno was also checking? So the question is, I don't know if someone from the agencies is here, but the thing is that, of course, we are when we talk about ESA, we're talking mostly about the polar orbiters and the products that come from there. The thing is that will the Meteosat, even the sounder, solve the problems for vertical profile on moisture for what we need for precipitation or not? So do we need to still go forward on precipitation estimates from polar orbiters in the future? So in terms of that was one of the questions that I still have in my mind. I don't know if anyone wants to comment on this or not.
Just to support what you said, is that maybe we need more exercise that you just saw, like on a particular basin or situation, comparing different sources of precipitation. And because obviously dedicated satellite missions are very important for precipitation, I think that there is complementary techniques between IR and Meteosat third generation, but two microwave radiometers that can provide precipitation under any situations, but with a larger spatial resolution. But I think that there's also the question of, are we talking about very large hydrological basin, where probably satellite will be sufficient. But from what I understand of the needs for flood forecasting and so on, sometimes the basin is very small, plus mountains and so on. So it's obviously a difficult situation. But again, support the multiplication of just what you presented, maybe in different regions, and again, having probably more dense in situ networks to kind of trying to have a ground truth, which is only a truth, not the truth. But it will allow to probably having a better picture of yet what we have now and what we'll need in the future. So multiplying this kind of exercise, maybe in 2 or 3 different sites, would be very interesting.
And I can add that you have also the urban issues. So it's not a big basin, it's just small cities, villages that can have really big problems and in very narrow areas. And this comes to your presentation also. You're talking about these GNSS systems. Kind of how close do we need them if we want to test them? Do you have an idea? I didn't ask for in that moment, but I can ask now. How close should they should be from each other to be useful?
I passed the last months looking at my precipitation gauges delivered by the weather station, and it's incredible how it could be very different in a kilometer area. Very different from what you have on nowcast weather prediction, also with comparing with radar. So at least we need something at least of a kilometer, but I would prefer something below that. Like when I say dense, I think about many station every kilometer square or something like that, because it's varying a lot. Especially we are looking for extreme events, large storms, and especially for convection cells, it could be very located and very different accumulation. Again, I'm talking about a very small location, but yeah, we need something below the kilometer.
I can support that, because sometimes we also have issues on the observations from the surface. I showed the 600 millimeters in 24 hours, which we had a lot of suspicions, but we didn't have anything to tell us yet that we should remove it.
Exactly.
And should we remove it from our archive, or should we not? So it's clearly an issue, and if you have a very dense observation, even if they have problems also, that would be nice to see the gradient at least. There is a bias for sure, but you could have a gradient.
And I want to emphasize that because there is yet some national network for GNSS which is working very well, is still used even in non-WP assimilation, so there is something there, but I think it's more like 10 or 20 kilometer separation. And probably, I don't know if you remember, but there is a map of over Germany. And using this already existing network, it was kept, the author of the paper was capable of mapping some gradients of the variation of extreme precipitable water vapor. So we could do something at this scale for now, but we definitely need to be at a smaller scale.
Okay. Any more topics that you want to discuss? I have another comment on the snow, because as you know, I come from Portugal, and you may think there is no snow here, but there is a little bit. And it's also an issue for us, not being like these big mountain systems that you have that was shown to be very problematic. But to support the mission on snow, I can tell you that you can also include there the less frequent places, or where it snows less frequently, as an issue, because as it is less frequent, we are less prepared. So the impact can be large still, and it is. So the risk issue is not related just to the intensity of it, but to how rare it is and how prepared you are. So for the mission on snow, and there was a question there to probably kind of give more interest on snow, you can also include, it can also be included the places where snow is less frequent. That was a comment on my side. I don't know if anyone from the snow part wants to comment.
No, it's not from the snow, but more from the rain. In the idea of multiplying the number of sensors, in situ sensors, I was wondering, now you have more and more individual, I don't know the name, weather station you can buy, and then you can put your data on the internet, and you have several brands doing that. So you have a network of a lot of rain gauges, like I know in France and all over the world, you have this Netatmo weather station, and you can. I have one at home, and I put my data on the net, and you have a nice network in Europe, in the US, and many countries. So is it interesting? Why you don't use this type of data?
Yeah, now there is various different things. For instance, for the there is also a Davis network. The purpose here is what I really need the precipitation to be very consistent with the GNSS station. So it's 30 meters. And when you look at the Davis network, for instance, the closest open station is 20 kilometers far from the station. So yes, it could be used, but in terms of precipitation, you really need something very located. Yeah, 10 kilometers is, for instance, I tried to do the same thing using the national network and some open source rain gauges, but I couldn't find couples with a distance below 5 kilometers. So yeah, we could use some opportunity result, but I think we didn't densify that in a way or another. But it's very interesting source of information, obviously.
Can comment on that too. Maybe on the Portuguese Met service, we are also integrating other networks outside the service, and also in Madeira there was another map that I didn't show that was kind of going to pointing the second extreme on the first event, and we are doing it also in the mainland. the issue here is that you have to stay with the entities that are going to stay. So if you just install a station and then you leave your station there and then you put it into somewhere, and in 2 years there is no maintenance and it stops, so it's not worth it. So you have to stay with the entities that are really needing it, and they will stay for long, so you can bother integrating it into the network. So I can tell you that nowadays over the islands and mainland, in our system we have our network, and next to it we are having other networks from external entities, and I think it's increasing and will be increasing. But nevertheless, it will not solve that problem of high precipitation with a very strong gradient on the values. So you will still have issues and problems knowing how much did it rain really. So it's still an issue. Of course, for the satellites, it's larger pixels, but we have to increase there too. It's key. Maintenance is key.
Anyone else? Any other thoughts?
So we are not, yeah.
Maybe I just come back to your question, what is coming or going on with snow missions. So I can update you on this. So actually, since 20 years, there's a lot of efforts towards a mission which is measuring snow water equivalent directly or indirectly. So NOAA made a very nice overview graph, which techniques are applied. And there are currently a lot of R&D projects going on into this direction. So what is very close in time is actually these L-bands are interferometry, what I quickly introduced this. So we are hoping for NISAR and later on ROSEL to come. But there is also another Canadian mission which is in preparation. It's a KU band mission applying a different technique. Other techniques which are currently evaluated is pointing towards Ka band. So this is at 35 gigahertz, looking for single pass interferometry and measuring snow height very accurately. So airborne demonstrations have already been done. And something what I think is very interesting in general for hydrology is a kind of geostationary SAR. There is a mission proposal going on at the Earth Explorer 12. It's already submitted. And geostationary SAR will provide you continuously images all over the day. You can focus the images depending on the resolution what you need. And this is not only for snow interesting, but also for monitoring floods, for looking for water vapor in the atmosphere, and many other parameters. And this is a very interesting mission. I know that the Chinese just recently launched such a mission, but the access to data is questionable, or I don't know. But also something in the Europe is in the Earth Explorer call has already submitted a couple of times. So and it's resubmitted just I think 2 months ago for the last Earth Explorer call. Just to keep you updated on that.
Okay, thank you.
I'm absolutely not a snow expert, but you intend to use SWOT data because you called about Ka band and SWOT is Ka band. Yeah. Yeah, it's coming in January.
Okay.
Yeah.
Yeah. Are we happy? I guess
If
we are.
there is any other comments, we can close the session here. Thank you very much once again, and enjoy your coffee. Thank you.
Okay, so we can get started with this last session of the day. We have a very diverse session with plenty of different topics. I think that could be a good thing. I hope you can find your favorite dish in the menu. We're going to start with evaporation. Unfortunately, Bill Custis couldn't travel, but very fortunately, actually, Yun-Yan is going to cover. She's going to give actually the first and the second presentation, probably with a little break in between so we can have some questions. With that being said, Yun, the floor is yours. Thank you so much.
Thank you very much for the introduction. Hi, everyone. My name is Yun Yang. I'm currently an assistant professor at Mississippi State University. And Bill Custis and also the third author here, Martha Anderson, they were planning to come but couldn't make it at the very last minute. So I'm here to cover both of their talks. So you will see me again on Thursday. So actually, I was Martha and Bill's postdoc before I joined Mississippi State University. So I'm pretty familiar with their talk, and I will try my best to cover their talk. And if you have hard questions, please leave them for Bill. And if you have easy questions, I probably can answer it. Okay. So the talk here is about the two-source energy balance model formulation using thermal infrared remote sensing of evapotranspiration estimation. And we are going to talk about some applications from field to global scales. So instead of the other sensors we touched in this meeting here, we're going to focus on the thermal remote sensing. Okay, so I would like to start with why it's so important to quantify evapotranspiration. As we all know, ET is this critical part of the global hydrological cycle. And also there are studies showing that more than half of the precipitation actually returns to the atmosphere through ET. And this evapotranspiration process can take almost 51 to 58 part of the energy of net radiation. So the ET really determines the regional, even global water balance and impact hydrology, ecology, and also our weather. So how we estimate evapotranspiration using thermal remote sensing. There are a lot of efforts to try to simulate the whole system from soil, vegetation to atmosphere. There are a few examples here. One of those popular ones is the SEEP model, which is on your left. And also there's another model is a soil plant atmosphere continuum, which was developed by John Norman, Martha Anderson, and Bill Custis. So this one focuses on the soil and plant root function. So when we use these soil vegetation atmosphere transfer models, normally when you look at the left panel, it requires a lot of inputs. So when you want to apply this at regional or global scale, you will have this challenge about finding the right input. For example, the root uptake and also the infiltration here is hard to find for the regional scale, especially for when you're considering the complexity of getting the irrigation data. So at the other perspective is we can use the energy balance and the land surface temperature to solve the vegetation water use on the land surface and highly rely on the thermal remote sensing observations. So this energy balance approach provides us a new metric that we can estimate the land surface evapotranspiration. But there are still challenges. So these challenges about using the thermal remote sensing to estimate ET, there are a few of them. The first is the interpreting the thermal remote sensing data, the difference between the radiometric temperature and aerodynamic temperature, and also when you consider the view angle impact for the surface temperature. So this is one challenge. And another challenge is prescribing the accurate upper atmosphere boundary layer condition for the energy balance model, which is very important. It's hard to find the good spatial resolution of these upper atmosphere boundary layer condition that can work with the remote sensing data together. So, and other than these two challenges, there are also another whole spatial resolution issues. So the first is when we want to evaluate our ET estimation, we use the eddy covariance flux tower measurement, which covers normally about 100 meters the footprint, and which doesn't really match with the very coarse spatial resolution of ET estimation. And another spatial resolution issue is in the application. So especially for agriculture applications, we want to look at the water use from each of the field. So if your ET estimation is too coarse, it's just you cannot see the clear signal from individual fields. So in the following a few slides, we'll talk through the solutions for these challenges. So first, the thermal remote sensing data interpretation. Okay, to solve this challenge, what we do is we get this two-source energy balance formulation developed. So we partition the radiometric temperature into the soil and vegetation component. And also at the same time, we'll consider the off-nadir thermal imagery impact in this first formulation here. And also in the bottom middle here is the system equations for the two-source energy balance model. We call it TSAB. So the key point of TSAB is we prescribing the initial latent heat, which relate with the ET. We prescribe this latent heat with the Priestley-Taylor equation, which is on the top right over here. And this original formulation for canopy transpiration. And we can adjust this based on the stress. And the information comes from the soil and vegetation temperatures. And as the whole system, the soil latent heat is computed as a residual of this energy balance system. So this is the TSAB formulation. With this two source, considering soil and vegetation, we can estimate the soil flux and vegetation flux individually. Okay. And that's the first challenge about the radiometric temperature and aerodynamic temperature difference. And the second challenge about prescribing the upper atmospheric boundary condition, the way we do it is we combine the TSAB we just talked about with a simplified atmospheric boundary layer model. And in this model, we estimate the radiometric temperature change in the morning transition, and also at the same time, we will look at the heating of the upper atmosphere. So combining these, we don't really need the observations about the atmosphere boundary condition. And instead, we can use a system of equations to estimate this. So combining the TSAB and also the atmosphere boundary layer model, this is the ALEXI model. So the ALEXI model is on the regional scale, and we use geostationary data as the input to look at the morning transition signal there. So that's the second challenge. And for the spatial resolution challenge, what we do here is we further disaggregate what we get from ALEXI, which is normally about 4 to 5 kilometer ET estimation. And during this process, we use the input from finer spatial resolution satellites. For example, we can use Landsat data, we can use Sentinel data, MODIS data, and also recently the EcoStress data into the system to disaggregate what we estimated from ALEXI model. And also doing it this way, we can make the energy conserved at both the spatial resolution. So now from like the last few slides, we actually solved the challenges we listed before. So the first challenge, the interpreting thermal remote sensing data, we introduced the two-source energy balance model, which is TSAB, partition the soil and vegetation component. And the second challenge for the upper atmosphere boundary condition, we coupled the TSAB with this ABL model, atmosphere boundary layer model, and so that we can solve this upper boundary condition, use equations. And this is ALEXI model. And for the spatial resolutions, we use the flux disaggregation, which is the dys-ALEXI. So up to now, we kind of like introduced the series of model development, which is ALEXI, dys-ALEXI, and TSAB. So you probably know how these three models link together now. And we can actually put many different satellite inputs there. As I just mentioned, the geostationary data, Landsat data, MODIS data, all of these actually, they come with their own spatial and temporal resolution. So when we use them in the system to estimate evapotranspiration, your evapotranspiration is also at this corresponding spatial and temporal resolution. So how we can get a good resolution we want, especially for agriculture, what we are looking for is 30-meter daily evapotranspiration estimation. How we can get this with all these multi-source satellite data, we fuse them together with a data fusion method. So this data fusion method is called STAR-FM, which was originally developed by our colleague Feng Gao. So with this data fusion method, we can leverage the possible satellite sources together to use them all together to get to the 30-meter daily ET estimation. So after this, we will start to talk about some of the evaluation and application efforts using the ALEXI, dys-ALEXI, and TSAB model. So first, I want to show you some of these highlighted sites that we have tested these model system over a wide range of managed and natural landscapes and very different climate types. As you can tell here, we have worked on the Vineyard, which is our GREEPAX project funded by NASA. And also we have corn, soybean in the Corn Belt in United States, and also some of the loblolly pine plantation. And when you look at all these highlighted sites, we also have them in different climate regions. For example, we have this desert areas in this tested sites. So following this, I will show you two of the recent efforts of using these model system. So the first one here we want to highlight is there are already efforts using Sentinel data to estimate evapotranspiration at field scale. So this is the published paper, look at the field scale actual evapotranspiration using Sentinel data. So this is already available, and if you are interested, you can look at that paper and find it. This is a few figures from this paper about the evaluation of the TSAB model. So For these different vegetation types and also the semi-arid and temperate climate zones, you can see that TSAB is doing a reasonably well job estimate the energy flux components over these sites. And another recent work that we want to highlight here is a recent effort to implement TSAB model into Google Earth Engine. And also in this work, compared the TSAB performance with a single source model performance over many sites globally. So this is work done by Hardy Jafar. And these are all the sites that he did the evaluation comparing TSAB and a single source model. So these are the figures from the paper that these are the statistical metrics and showing the comparison between the TSAB model, single source model, and observations. So the first row is RMSE and then MBE and percentage of biases. Here, how over most occasions that TSAB outperforms the single source model. And this is highlighted by these red and green arrows on the top. So the red color means where the TSAB works better than the single source model. So you can see how it outperforms the single source model over multiple climate zones and different biomes there. So this is the reason is due to this partitioning of the radiometric temperature into the soil and vegetation component, which is not existing in the single source model. Okay, so based on what we just talked about, that thermal remote sensing is a very important component of these model system. So the recommendations here is we really need, it would be great if we could have more frequent and high resolution thermal infrared observations. And when we look at what we already have from the satellite observations at different spatial resolution, we have like MODIS, eco-stress, and for the future missions, we will have Trishna, OSTM, and also SBG. So it's really exciting to see that in the future, we'll have a lot more thermal images to work on. And but before we get to that stage, there are times that we have only limited thermal imagery sources. So one possible solution is we can consider the collaboration between the public and the private sectors. Here is an example of the Hydrosat. The Hydrosat is building and preparing the launch of a constellation of thermal satellites that will provide about 30-meter spatial resolution images. So combining all these public available and private sectors thermal images might be a solution that we can get more thermal images to look at. And we want to highlight a successful public and private partnership that is a very large project happening in United States. The name of it is called OpenET. So actually my talk will talk a lot about OpenET. So this is really a good transition slide that Bill put over there. And it's just the goal here is we want to provide this open access field scale evapotranspiration data to the end users. So they can really get this information and use it for their everyday like irrigation scheduling, policy making. Yeah, so as a conclusion, the land surface temperature, which is a thermal observation, can be used for monitoring changes in water use with changing climate, land use, and population, and also can improve hydrological monitoring to better cope with the climate extremes. and also can improve accounting of current water use and crop water productivity, and also can help with the crop stress detection and yield estimation. So this is a quote Bill liked to use. We cannot manage what we cannot measure. And we also want to highlight Martha's talk on Thursday morning. Her talk will be focused on the global ET estimation effort. So if you're interested, please come back for that, although it will still be me giving that talk. Okay, so with this, I'm going to conclude this talk, and I will try to answer your questions. If I cannot answer it, please direct that to Bill. And also remember to mention to Bill that I did a great job. Thanks.
Thank you so much, Yoon. Are there any questions? If not, I have a question, actually. It's not a difficult question, but it's a mean question, though. So I can see the use of thermal for evaporation for agricultural applications and water management. You started talking about the importance of evaporation for climate at the beginning of a talk. You said more than 50% of a precip goes back into the atmosphere. And we know that about somewhere between 10 and 20% of evaporation is actually interception loss, right? Like rainfall interception loss, which happens when it rains, and it rains when it's cloudy. So how do you see that as an issue? The fact that you may not have land surface temperature observations when interception is happening, which is really a very powerful flux.
Yeah, this is actually is a question that we got a lot, actually. So what we are thinking about this is because we highly rely on the thermal signal. So we really think, a lot of these signals should exist in the temperature changes we observed from the space already. And so that can be a signal that can somehow help us to address part of this issue. But I'm sure this is a answer might not satisfy you, but we can discuss more offline.
Are there any other questions? If not, thank you so much. And we welcome the second speaker, which is also you. You don't have to come out and in again. So Yoon is going to present also the OpenET platform. And yeah, thank you again for taking over all the talks so far in the session.
Okay, so me again, my name is Yoon Yang. This is my own talk. And also, I really think, the way we schedule the talk is really helpful because Bill's talk already put a lot of these basic information of different thermal models there. So what I will talk about is how we put these models into the Google Earth engine in the cloud computing, and how we see it's a necessary move forward step, and how we see this can help us. So here, I'm going to talk about the evapotranspiration estimation with multi-source satellite data in the OpenET platform. Okay, so what is OpenET? I'm sure probably some of you already heard about this. So this is a really a large project, a very collaborative effort from multiple agencies and universities and institutions. So why we have the OpenET and what OpenET is doing. So let's start why we want to have this OpenET project. So with the increasing concern of water and food security and increasing amount of population, and we see more of these climate change signals, it's really critical to better manage our water resources. But before we can manage this, we first need to know the water use condition, right? And as agriculture is a large water consumer sector of the water resources, we want to first know how these waters are used in different regions, different years, and how this water is used from different crop types. So with the development of the thermal-based evapotranspiration models developed over the last few decades, that we have this relatively mature method there, but still is normally constrained to a small area because it's constrained by the computational power. So you don't get to run a large area. So this is an issue there. And also, this ET data is normally used in the scientific community. It didn't really get into the hand of the end users and the stakeholders who really need this information to make the policy making, to make irrigation scheduling decisions. So the goal here of OpenET is, okay, if we have the computational power constraint at local server, why we don't put them in the cloud? So at that time, Google Earth Engine start to develop. So we will see, okay, let's try the Google Earth Engine. And that's first thing that we will try to solve the computational power limitation. And another thing is, with this, actually, we can save the data on the cloud, and we can make this data easily accessed by the end users and the stakeholders. So the goal of OpenET is we want to provide this field scale evapotranspiration to the end users and the stakeholders. So we want this only that time available to scientific community, this ET data available to everyone, and can really help with the water management and the prescription and the precision agriculture. Okay, so for the OpenET, because of the ultimate goal there, from the beginning of this project, we have been guided by these main goals, like we want to provide reliable and easily access ET data. We want to build trust in this data. And ultimately, we want to provide a variety of sustainable resource management practices that enable at a scale that just wouldn't be possible without OpenET. So we've recognized that from the beginning how critical the middle trust component is. So actually for the OpenET project, when we first started, we started with talk to the end users and the stakeholders. And we worked with over 100 farmers and practitioners, water managers, to know what they really need. And once we know what the end user and stakeholders needs, and we come back to start to build our system. So with this system, we really want to help with different water resource management and natural resource management practices and projects. For example, the rural communities to design local-driven water conservation, and also help with the water managers to develop more accurate water budget, and help with the policymakers to make a better solution to help with the regional water resource management. And also, the last but not least, OpenET really want to help farmers, even individual farmers, to improve irrigation practices and help them to reduce the cost for fertilizer, water, and energy. So after all these, it's just how OpenET, we want it can serve our real, community as a citizen science. So how OpenET really works. So the way we do this, build up the system is we use the Google Earth Engine. Because Google Earth Engine already have most of the data we need, meteorology data, satellite data, they're already loaded in Google's engine. And there are some of them that are not available there. We actually routinely upload those data that to help us do the modeling. And with the Google Earth engine, we actually also integrated our, where's my laser? Okay, so we also integrated our ET models and into this Earth engine using the Python API that Google Earth engine have. And this is the part that we produce the data. And we want to send this data directly to the end users and stakeholders. So the way we do it is, one is we have this user interface, is a web browser. So here is the address of it. And once you get there, you can look at the field water use from each of the field. And I will later show you a few examples of that. And for more advanced users, because we do consider there are large like farmer groups or even scientific communities that we need more data, so they can use our API to automatically extract the data they need. So this is how the OpenET really works. And here I mentioned ET models, because for OpenET platform, we have more than one ET model. So the Alexi dyslexia we just talked about is one of the 6 models. And we also have other 5 models, the EE metric, CBOB, SIMS, PTJPL, and CBO. So these are 6 well-established ET models that we are operationally run all 6 of them. So there are questions, you know, which one is better? So we also understand that the end users, sometimes they don't want 6 numbers. What they want is 1 number. So what we did is actually we also compute an ensemble value for the end users. And we did a very careful evaluation for the first phase. And this paper already published, led by our project manager, Forrest Melton. So this is, in this paper, what we want to highlight here is when we compare the model performance with the Flex Tower observations, and we notice actually the ensemble is the best, which is, you know, we are all happy to see, because this is just the power of using multiple ET models together. So this is the first phase of evaluation. We actually also did a second phase of evaluation of this. In the second phase, we further involved 72 additional Flex Tower sites. So in this second phase of evaluation, we have almost 150 Flex Towers all over the United States for the evaluation. So the first paper led by Forrest Melton, that was, this is the first phase of evaluation. And the paper for the second phase of evaluation has just been accepted, and you will hope you can see it soon online. So this is the way that we really try to build the trust with the end users. And this is the user interface that we want to make the accessibility of ET data easier for the end users. So the OpenET uses all this publicly available data from multiple satellite and weather stations and bring that in Google Earth engine and calculate the ET and provide this to end users. So when they get to this website, and they can actually look at the field scale at this, and each color, like here is a field. And when you hover over this field, you can see the time series of monthly ET over this site. And we actually just had a new API system. So from that API system, you can directly download, this is monthly. From that, you can also download the daily ET data there at 30 meter. So this is, really convenient for a lot of users. Farmers, they can directly hop on this website to look at the water use information. And this is an animation to show how the OpenET website can look at the water use from each field, and anyone will be able to get this information from the website. And when you zoom to the certain level, you will be able to look at the water use information there. And so far, the data we have is from 2016 all the way to 2023. It's operationally running. So whenever there's a new Landsat image, we will have a ET estimation there. Okay, so that's the basic structure of OpenET. And here is my group's effort that we want to introduce multi-satellite information into this platform. So before this, we want to just highlight a few of the land surface temperature observations that we currently have on the top, which is GOES, MODIS, WIRS, Landsat, and EcoStress. And we are using somehow like a different level of these LST measurements in the system. And we highly rely on the Landsat data because Landsat is just, it has both the thermal and the V-sphere band. So we can get the temperature observation and the vegetation indexes from just one satellite. And for Sentinel, it doesn't have thermal for now, but we can still use it to get the vegetation indexes. And what my group is currently doing, funded by the NASA EcoStress project, is implement the EcoStress data into the OpenET system. And looking into the future, as we can tell at the bottom here, these are the future land surface temperature observation missions that we want to learn from, implement EcoStress into the OpenET first, and get ready when there are more of the thermal data ready to use. So here, so far, we highly rely on Landsat, but my group's work is we want to implement EcoStress into this. And while we do this implementation of EcoStress, we also use the Sentinel data. And how we use it, here is the reason that we use it. First, for Landsat, this is what we normally use for Landsat. We sharpen is 120 meter spatial resolution of thermal data based on the V-sphere band from Landsat. So we can get 30 meter observation of the LST. And also for EcoStress, you can tell it's about 70 meter spatial resolution, but the goal of the OpenET is providing 30 meter. So we need to sharpen this 70 meter EcoStress observation. And the way we do it is we use this data mining sharpener, also developed by our colleague Fengao. We actually already successfully implemented this into Google Earth Engine so that we can do it on Google Earth Engine. And here, when we do the thermal sharpening, we need the vegetation index, the V-sphere band, to help with the sharpening. And the way we can get it, we can choose to only use Landsat. But considering Landsat, the revisiting time is 16 days. So for a cloudy region, you may not have a close enough Landsat to use pair with the EcoStress data. So what we do here is, here we include Sentinel data to increase the V-sphere band observation frequency. And the way we use it is we based on this harmonized Landsat Sentinel product. So this includes both Landsat and Sentinel data, which has been go through the same atmospheric correction, the same mask, cloud mask, and all these processes to make them consistent. So we are using this to help with the sharpening. And just like example of this sharpening. And we have the Python code. We also have the Java code to just play around. And this is the sharpen results. This is not. This is the EcoStress original. The native spatial resolution is about 70 meter. But if it's off nadir, it can be coarser than that. And this is the sharpened results. As you can tell that we really get the detail of each of the field from the sharpening with the help from Landsat and the Sentinel-2 data. Okay, so like the before, after, it's really a difference there. And then we use this sharpened OST into the OpenET system to produce the ET data. So here we can see the first row is from Landsat, second row from EcoStress, and first column is the original LST from both of them, Landsat, EcoStress, and this is sharpened Landsat, EcoStress thermal observation, and these are the ET that we estimated from these two different thermal sources. I specifically choose the same day image to clearly see the difference there. So as you can tell, they from both the value and also the spatial pattern, they are very consistent. So this is a part of work that we are currently doing. And we are actually further developing very high resolution applications based on OpenET, specifically for the agriculture that with complex structure. For example, the vineyard, the orchard, you have the middle row, then you have the row of vegetation there. So 30 meters, sometimes you don't really separate the interrow and the row. So what we do is we are introducing the planet data into this system, but this will not be operationally run to get the results. But the goal here is we will develop a method that the community can use. And when they have an interested area, they can have their own planet data ready and then can run our methodology to get the 3-meter ET estimation. So the method we are doing with this is we are using a deep learning model that we train based on the OpenET 30-meter data and also the Landsat spectral information and also planet spectral information. So we are testing it over the California sites where we have both the vineyard and also the orchard that we can test whether we are doing a decent job, improve the spatial resolution and compare with the UAV observations over this. This is a manuscript that my postdoc is currently preparing. Okay, so now we talked about the entire system of OpenET. We talked about how it currently uses Landsat, but we are working heavily to bring the EcoStress and Sentinel data in, and also the planet scope data. And when we look into the future, in Trishna data or STM and Hydrosat, we really want to build a foundation that makes this system accessible to these different thermal resources. Okay, so as a conclusion, so the OpenET provides accessible, accurate field scale ET for stakeholders and end users, and the potential of implementing multi-satellite observations into OpenET platform for improved ET estimation. And for the recommendations, I totally agree with Bill's recommendation that we need more fine spatial resolution thermal observations. And also, I think we also talked about something in the keynote that we want to consider the interactions between the different components of the hydrological cycle instead of considering each of them as an isolated part. And also, I think the international partnership can leveraging the collective expertise and the data together to further improve our understanding of the hydrological cycle. So for the international effort here, I want to briefly mention one of the efforts we are currently doing under CIAS, the land productive validation subgroup. So we are establishing a new focus area on ET. So for the land ET product validation. And we have two leads, normally one from US, another one from Europe. So Carmelari from University of Milan and myself will serve as the co-lead of this. And we will soon reach out to the ET community to look for suggestions, recommendations to help with preparing this ET validation protocol. So with this, I'm going to conclude my talk and thank you very much. And this is it for today, but you will see me again on Thursday.
Thanks, Yoon, for the interesting talk. So we have time for one question from the audience. Just, please.
Yes, so thanks for your presentation. I really like the OpenET initiative.
Thank you.
Do you have any idea of how many people actually use this data on a daily basis?
Yes, I do have that information. So we first launched the first version of API, and for that API, we got more than 10,000 registered users. And we just launched a second version of the API back a few months ago. And just inside of these 1 or 2 months, we already got about 4,000 registered users. So these are the users, you know, we don't really know. We kind of like know where's like a large region they are from, but we don't know the individual of them. And other than this, we actually have a lot of collaborations established with the state governments and also a lot of the private sectors for using of OpenET.
A quick follow-up from the used question, because I'm curious. Do you have an idea of the feedback of farmers on the catalog?
We do have ideas about the farmers' feedback, and that will be a very long story, actually. But let me put it short, is some of them, they are very happy of them, the data, because they can really look at and the water use of their field. And also some of them, they do have questions. Of course, we do receive questions about the difference they see from what they expected and also the data from OpenET. But the good thing is that we will soon have a user and application workshop early next year that will further, you know, listen to the feedbacks from the users and further improve the system.
Thanks again. So no more question. We can move to the next speaker, which is Soraya Romao with a talk about bathymetry.
Good afternoon. My name is Soraya Romão. I come from Colab Plus Atlantic, and my work is about assessing the influence of nearshore bathymetry on coastal overtopping due to extreme sea level events, a satellite-derived bathymetry and X-beach modeling approach. This presentation will follow this sequence of topics. This work was developed under the project EO@Sea, is funded by ESA, and we have some, where is? Okay, it doesn't work. You have some partners, and one of the main objectives of this project is to understand the application of Earth observation techniques in the comprehension of the process related to coastal hazards, namely extreme sea level events, and to study the effect of compound events. So the extreme sea level events represent a great dangers to low-lying coastal communities, generating coastal erosion, flooding, overtopping, and some structures destruction. As you can see in this picture, we have demonstrate the passage of storms along the Portuguese coast. The wave process are controlled by the beach morphology. We have two beach profiles, one more dissipative with less inclination, and one more reflective with a sandbar. These different profiles contribute to the wave to break further or closer the beach, and the bars will contribute to have a higher dissipation of the waves when getting closer to the beach. These aspects are important when considering extreme events as storms, and in the scope of this work, the focus is about these interactions with the occurrence of wave overtopping. The wave overtopping corresponds to the amount of water from the waves that pass over the structure, like the breakwater or seawall, and whose the crest is higher than the still water level. For this work, it is important to understand the dynamics and the complexity of these environments, particularly under these conditions. And it's fundamental to have tools to permit assess these events without field data, which are in very difficult conditions and costly to acquire. So as the main, in this work, we will combine the application of a method to estimate satellite-derived bathymetry and the validation with measured field data, and use the satellite-derived bathymetry with numerical modeling. In this case, we use the X-Beach to study extreme sea level events. As objectives, we pretend to know how beach profile or the submerged bars influence the occurrence of overtopping, and what are the physical processes responsible for the occurrence of these events. The study area is in the Caparica. Caparica is a beach located in the southern coastal region of the Tagus estuary. As you can see, is not very far from where we are, and if you have the opportunity to visit, I really recommend. This beach is a urban beach and highly populated for leisure activities. So it's important to its study and the coastal defense. In terms of hydrodynamics, is as a mesotidal regime and is exposed to an energetic wave climate, where we have significant storm events that reach with severe problems. As you can see in the video, is an overtopping event that occurred during the passage of Hercules. And in the figures below, we have severe coastal erosion and the damage of some structures and the walkway. This beach suffers from severe coastal erosion. It's regularly subject of artificial sand nourishment interventions, which reduce the vulnerability to extreme sea level events and alter the nearshore morphologies. Getting into the methodology, in terms of the satellite-derived bathymetry, were used Sentinel-2 imagery with a spatial resolution of 10 meters. And you use several images. In this case, I will only focus on the image from December 2018 and January 2021. The processing of this image was using the software Acolyte to make atmospheric corrections. It was done the classification of the bed grain size, the determination of sediment reflection coefficient, some corrections of the water column, and the bathymetry was determined by optical inversion satellite-derived bathymetry. These steps of the processing were performed by our colleagues from Telespacio. From this processing, we get topobathymetry data and profiles. They were compared with measured data from Cosmo. This is a project of the Portuguese Environmental Agency. And the profiles extracted from the bathymetry was used as input in the numerical model. In the XBeach implementation, we used 3 different beach profiles. The first one is a profile from 2014, and is considered our benchmark case. The second one is the profile extracted from the satellite-derived bathymetry from 2018, and is characterized by a submerged sandbank located further from the coast, as you can see in the picture in the right. The third profile is from the satellite-derived bathymetry from 2021, and is a post-nourishment intervention. In terms of wave conditions and water level, it was considered 3 storm events that caused some damage along all the coast. The storm Hercules from 2014, the storm that occurred in February 2017, and the storm Emma that occurred in 2018. The conditions, the wave conditions are represented in the table, and the water level was the maximum water registered in the wave bay due to storm surge. The analysis and the simulations profiles correspond to P6. There is with there you are. There is with the here in the red circle. In terms of implementation, the model was previously calibrated and validated in the work in Garçon et al. 2023. The numerical bathymetry has a variable spatial resolution from 4 meters in the offshore boundary and 40 centimeters in the subaerial beach. The model runs in non-hydrostatic mode. This mode permits to propagate wave by wave to assess this transformation from the offshore to the coast. The wave conditions and the wave spectrum generated by the XBeach was the same for the 3 beach profiles. And the model ran 2 hours. The first is warm up, and the second hour is used to the results. As outputs from the model, we consider the discharge and the water level. In the analysis, the water level is, we perform a spectral analysis to extract wave height, high frequency, which correspond to short waves with periods below 25 seconds, and low frequency, also known as infragravity waves or long waves, which are represented by wave periods above 25 seconds. In terms of results, the satellite-derived bathymetry was estimated for depths up to 10 meters. And as you can see in this figure, in the figure in the right, we have the measured bathymetry, and sorry, the figure in the left we have the measured bathymetry, and in the right side we have the satellite-derived bathymetry. And we can see that the bed forms are well captured by the satellite-derived bathymetry in all over the analyzed area. Both figures are from December 2018. The profiles extracted from the satellite-derived bathymetry were compared to measured profiles. The profiles in the left are from 4 to 10 meters depth, and in the right are the 3 to 8 meters depth at profile P6 and profile P7. The statistical analysis, we obtain an overall accuracy better than 1 meter, and the best estimates occur for depths between 2 and -5 meters. Getting in the characterization of the overtopping events, these plots show the occurrence of the events. In the x-axis, we have the time. In the left y-axis is the discharge, which represents the volume of water in the point that there is marked by these arrows, is over the structure. And the right y-axis is the accumulated volume along the simulation period. So in terms of identification of the events for 2014 bathymetry, were identified 4 events. For the bathymetry for 2018, 6 events, and the bathymetry for 2021, only 3 events, half of the previous one. For the event, the storm event of February 2017 was detected 1 event for each bathymetry. In terms of the accumulated volume, the overtopping volume is lower for the 2021 profile, and the volume is higher to the bathymetry from 2014 and 2018. Storm EMA is not here represented because no non-overtopping event was identified. Here I present the wave height along the beach profile for the 3 profiles and for the 3 storms. As the behavior is similar for the 3 storms, I will zoom in. Wrong button. And here we can see the black lines correspond to the profile benchmark 2014, the red lines correspond to the profile 2018, and the blue lines correspond to the profile 2021. Higher dissipation in wave heights occur over the sandbar and at the beach, and they are thoroughly dissipated. Sorry. Wait. And they are thoroughly dissipated when reaching the seawall. Profile from 2021 promotes higher wave energy, while the profile from 2018 dissipates less when reaching the beach. Here I present the high and low frequencies and the water depth in the base of the seawall, and the discharge over the seawall for the point showed before. Yes. Here I only represent a block of time of 500 seconds. And in this case, we can observe for the benchmark profile 2014 and 2018 occurred 2 overtopping events for the same at the same moment, while for the profile from 2021, only an overtopping event has occurred. And here is a zoom from one of the bathymetries, and you can see at in the black line correspond to long waves, and the correspond to the long waves, and we see that the sequence of higher long waves contribute to increase the water depth in the base of the seawall, and that's what contributes to the overtopping occurrence in both events. And to finish, here we calculate the difference of high and low frequencies between the benchmark profile and the profile is extracted from the satellite-derived bathymetry. The difference from the high frequencies are very small. However, the difference of lower frequencies indicates that there are a small increase. Disappear again. Okay, there are a small increase in the panel from the left, the red circle, a small increase in the long waves near the seawall, while for the difference from profile 2014 and profile 2021, there is a higher dissipation in when the long waves reach the seawall, which means that this bathymetry contribute to higher dissipation and less energy will reaching the seawall. As conclusions, the methodology to derive bathymetry from satellite imagery retrieve accurate results with errors below 1 meter. The numerical model accurately predicts the occurrence of extreme sea level events. The beach profile affects the occurrence of the overtopping. More robust profiles decrease the occurrence of extreme sea level events. Infragravity waves and the water accumulation at the seawall toe are the main forces contributing to overtopping. And the combination of these two methodologies improve the predictability capacity of extreme sea level events and the associated impacts. In terms of outlook and recommendations, we would like to highlight to enhance the existing environmental monitoring programs through the integration of satellite-derived bathymetries with ongoing in situ observations, the integration of updated bathymetric information with operational warning systems to improve the capacity to accurately predict the occurrence of coastal overtopping, and integrate the satellite-derived bathymetry and morphological data in funded research programs that contribute to sustainable development and environmental conservation. Besides the ESA that funds this project, thanks are due to Portuguese Environmental Agency for the topobathymetric data from COSMO program. You can also visit the poster number 115 about this same work, and thank you very much.
Thank you so much. Thank you, Soraya. Are there any questions from the audience? If not, I think we're running quite behind schedule, so I'm going to thank you again, and we're going to move to the next speaker.
Thank you.
That's Tim Trent from the University of Leicester, and he's going to be talking about water vapor in the troposphere.
Hi there. So yeah, today I'm going to talk about some development of novel tropospheric water vapor products, which includes stable water isotope logs that I've been doing for a few years now with SWIR sensors, and sort of show you some of the products and things we're doing. Okay. So the outline for the talk today is really, I'll go quickly through the sort of the motivation and the challenge about why we want to sort of do this, or what the point is really. And then because this is a hydrology predominantly workshop, I've got a quick intro into the remote sensing of water vapor in the troposphere, just to sort of highlight the novel aspect of this, and then go into sort of the stable water isotope logs and the products themselves. So this picture shouldn't really come as new to anybody, but essentially in the atmosphere, water vapor accounts for a really small percentage of the overall mass. But the fluxes, as we move through there to the transport of moisture within the sort of 8 to 10 day cycle is actually quite uncertain. There's these bigger uncertainties related to it. And one of the things that can contribute towards this is actually the vertical gradients of moisture through the troposphere, which can arise through things like convective mixing. So if we look at sort of the last sort of around CMIP, not CMIP 6, CMIP 5, sorry, the climate models show that as we have a warming environment, we get a strengthening of vertical mixing. This dehydrates the planetary boundary layer, reduces low cloud cover, and alters things like planetary albedo. In the analysis that was done with this, they actually show that this could have a climate sensitivity of more than 3 degrees Celsius for CO2 doubling. So it's quite a significant finding, and it also contributed for over 50% of variability within climate models. So again, it's quite unconstrained and a bit uncertain. So, so measuring water vapor in the atmosphere goes right back to the 60s. With Nimbus missions, where we have basically an infrared radiometer channel around about 6.5 microns, and this is sensitive to the moisture in our upper troposphere humidity, which is around about 4% of the actual mass. Very important for greenhouse effect and climate feedbacks, but doesn't give us any information on sort of structure or total amount. We move through into the sort of 70s and early 80s, and we start to see these satellites have more channels, and we also have the advent of microwave sounders as well. So we start to get total column measurements. So this is the whole atmosphere with the real weighting towards the troposphere. And it's not until the early 1990s where we have something called the ATOVS configuration, which is the combination of thermal and microwave, where we start to get crude profiles within the troposphere. So these are resolutions sort of greater than 3 kilometers. So it's not great, but it's sort of getting there. And it's not until we have the A-train in 2002 where we start to get the sort of the updated version of the ATOVS, where we now get things around 2 kilometers resolution. And this is what we continue to see today with things like Meteosat third generation, etc. But we also get the inclusion of other satellite sensors, which have high spectroscopic resolution, and they work in other parts of the electromagnetic spectrum. So we have UV, vis, near-infrared, and shortwave infrared. And because we can resolve these features, we can start to do some different things. So water isotope logs, they really allow us to assess and improve model-based representations of moisture sourceways and pathways in sort of Earth systems or climate models. And they can either do this by providing you information or providing a constraint in some way. So they can be used in sort of a different couple of ways. From satellites, we really get these from the infrared, and these are sensitive to the mid-troposphere. And in the shortwave infrared, we have column averages, but we have a real weighting towards the boundary layer. And the way we sort of represent this is with this delta notation. And what this really is the ratio of your isotope log, so in the case of something like HDO, to the actual water vapor in the atmosphere. And then that's normalized by a standard. And depending on your isotope log, you have a slightly different number. And what this really tells you when you sort of measure this delta is the sort of process that's gone on. So if we start from over the ocean, as we get evaporation, the lighter isotope logs evaporate preferentially. And as we move into the atmosphere, precipitation removes heavy isotope logs, and this essentially changes this sort of delta value. However, we don't use this alone. We use this in conjunction with the actual water vapor measurement itself. So they're known as water vapor pairs, and you can look at the information a bit like this. So when you have data in sort of this sort of area here, laser. You're essentially looking at what's above called the Rayleigh line. So here we can actually observe mixing processes, and you can actually see sort of differentials between mixing with land and ocean sources in very crude ways, just from by eye. And if you do a bit more detailed analysis, you can actually drill down into that a bit more. Below here, you get super Rayleigh. Below that, you get what's called super Rayleigh. So you can actually see microphysical processes through convection and clouds. So with infrared measurements, where you can sort of see more of the mid-troposphere and the clouds below, you sometimes pick up these as well. So there's quite a lot of information you can sort of bring together through satellites. But the processing chain that I work with really starts with GOSAT, which is probably unfamiliar to a lot of people here, because it's actually a greenhouse gas monitoring satellite, and you can think about it as actually providing sort of in situ style observations with the way it samples. There's an instrument called the TANSO FTS with 2 shortwave infrared bands. One of those is very similar to the shortwave infrared band on Sentinel-5P Tropomi instrument. And the way we work is we develop on GOSAT because it's a very lightweight data set, but has a long time series. And then we implement this within Tropomi, which has a shorter time series, but higher spatial resolution. And we get some sort of iterative cycle. And the idea being when we go out to METOP 2nd generation with Sentinel-5, we will have algorithms in place to sort of take advantage of this new data, which goes out into the 2030s plus. So the recent work really actually started with Tropomi in this cycle. So we took an algorithm from GOSAT. We made some updates. This is known as the University of Leicester full physics algorithm. It's an optimal estimation scheme, and it has been used for CO2, methane, water, isotope logs, solar-induced fluorescence. And what we do is we make a few updates for the spectroscopy because the window shifts slightly, and then with some new measurements made by DLR. We have a new solar model. There's some quality flag development and things like this, and we get these maps you can sort of see here. So this is our version 1 product, and you can sort of see, let me do this, just from the different colors. So in Africa here, in sort of January time, we have dry air coming in, and where you see these sort of yellow colors, we see heavier depletion, where we're getting mixing from the land surface. And in July, during the summer months, when the winds shift, you see the moisture air coming off the ocean, and you see these darker blue colors. So just by eye, in the first instance, again, you can sort of see these sort of processes happening. And then what we've also done is, because the vertical structure for delta depletion is really unconstrained, we include a bias correction, which is developed using sort of an ensemble random trees model. So we have this project with ESA, which finished 2021, and then we move into what's the next step? So we turn to GOSAT, because we now have over 10-year record, and we change this into a full profile retrieval from the previous scalar approach we were using, where we try to have a more informed view on what the profile shapes are. And we have 2 versions. One is a linear profile retrieval, and the other one is log. And the reason for doing a log profile retrieval is because it deals with these order of magnitude changes you have in humidity. And we co-retrieve the H2O and the HDO profile at the same time. And in version 1.1, the log one, we actually have an off-diagonal constraint. And this comes from another project, which was the Musica project, which was run through Karl Schur Institute. And what we can see here, so the scatter diagrams on the left-hand side here is the data as it comes out. And because we have this very loose constraint over the shape, we can see there's quite a strong bias here in the delta D. But the same model that we use for Tropomi actually does a very nice correction. So we have nice consistent data products between the two. And this is the GOSAT data it's seasonal rather than monthly, but we do this seasonally because we just have a lot less of it, essentially. But you can see they're fairly consistent, and you can see the similar lighter colors in sort of the winter months with the dry area, and the darker for the blue in the Sahara again. So one of the other key things you want to do with these things is you want to compare them to models. And what the log profile retrieval allows you to do is produce something called an averaging kernel. And the averaging kernel is essentially a smoothing function which allows you to transform your model into how the satellite would actually see it. And on the bottom row here, we have actually the first SWIR averaging kernels from GOSAT. So, and you can see from the different colors, these are just different seasons that they actually change based on the amount of information that's coming from scattered sunlight. So when we move into hemispherical winter summers, when you're in the summer, you get stronger signals, and when you move into the winters, you get lower. But it shows also that you can only use this data in certain times of the year outside the tropics, which is quite key. So other sort of novel products that have been developed through GOSAT as well is the ability to split the column, which you haven't been able to really do with non-thermal information before. So what we found in a 2018 study is that if we look at the information content through the column where we find the first degree of freedom, this actually is highly correlated to the planetary boundary layer. So we get a planetary boundary layer column. We also then get a free tropospheric column. And that's what's shown by these four maps here. These are just some seasonal averages. And on the right-hand side here, we can then look at the trends as well. So as I said in the beginning, we have this hypothesis that we will have a drying of the boundary layer as the climate warms. And looking from the trends, we see a drying in the tropics, where the tropospheric pump would be, and a moistening in the free troposphere. The caveat here is that these are very preliminary. However, as we start to refine the sub-column products now need to be validated quite carefully to make sure they are showing what we see. So that this could be quite an interesting finding if we prove it to be true. But the second step from this idea is also we can look at the ratio between these two columns and try and link it with this sort of delta Q here value if you were looking at sort of venting from the boundary layer into the free troposphere. So could you get extra constraining information for NWP? Again, this is quite experimental and it's sort of quite dependent, but this is the route that these are the products are going. And then the final piece of information we want to think is like, do we have any sort of link to specific humidity at the surface? So a couple of quick studies we did show there's actually quite a strong relationship between the planetary boundary layer column and surface humidity, and that worked over both land and ocean. So developed a model to convert the GOSAT boundary layer into surface humidity, and then this is then averaged together with the Hadley Center measurements over land and the ICOADs over ocean, and we get this sort of blended product here of both. And then more recently is bringing in other satellite products which have surface humidity and building a harmonization algorithm to join them. So we have a level. This is a level 4 blended seasonal product. Sorry. So this is what I'm hoping to have out in the next few months. This was a prototype, but with the new data sets coming from DWD and from NOAA, this potentially can run from 1988 to 2023. So some quite interesting analysis potentially to come out of this. There are a few artifacts which are coming from the harmonization algorithm, which manifest here, and this is just to do where we have breaks in sea ice, and I think some of the microwave measurements are, and we just don't necessarily have too many observations to ground them to. So it's that bit's a bit of work in progress, but don't think it's too difficult to deal with. But otherwise, it's looking very promising. So moving back to this sort of potential of isotopologs. So the sort of development GOSAT the idea is this starts to feed back into Dropomi, but in the meantime, what else can we do? So the next sort of step is to really combine the shortwave infrared with thermal infrared. So this Musica IRZ is a product which comes from KIT, and this is the averaging kernel. And you sort of think this is just where the information comes from. And when we combine this with Dropomi, we get something that looks a little bit like this. So we can see this increased sensitivity to the surface. And that allows us to, again, have more vertical information. It's still not huge. It gets around about just over 2 degrees of freedom. But this is a doubling of what we had before. And this is the kind of change that we see. So this is just a scatter diagram of the original Music-ESRIN, and then when we combine it and compare it at the same ground truthing site, we see an improvement in the relationship between the two. So this is the final slide, and this is a study we did within our Tropomi project with some colleagues in JAXA, and this is a synthetic data assimilation study where they looked at what were the benefits of assimilating the IASI humidity information with isotopic logs and the Tropomi, and both together. And the take-home message here is that this pink line is the result. This is the skills score or the skill improvement for a number of different variables, and the pink line is the combination of both. And we see that this is 20% to 60% improvement on the forecast all round. So this is potentially will have huge impact on sort of like a convective precipitation and other things within assimilation frameworks. However, the caveat again here, this is synthetic, and the sort of real results are to be still to be seen, but it's promising. So the outlook is is really quite promising. So we have a whole new bunch of information coming from new sensors, and this combination that we'll see on sort of METOP next generation with IASI NG and Sentinel-5 will probably drive reanalysis products going forward into the the next 20, 30 years. The recommendations sort of to come from this is we need continued support for in situ networks, and I think this probably goes for a lot of the talks through the whole conference. But for isotopologs, we have there's GNIP, TCONG, NDAC. They exist. Some of these places come under threat. We have new ones coming online, and we need this continuity of measurements to sort of ground truth everything. The other thing is we now getting to the point where we want to try and bring together sort of the atmosphere and the land surface, and isotopologs offer a nice mechanism to really do that, especially when we start to go from fast phase into slower phase sort of processes. And maybe something like a critical zone observatory would provide a good test bed for maybe bring these things together. There's definitely there's a potential for GWEX activities across GJAP and GLASS, because again, with the products, there's still no big holistic sort of oversight of how well they all do compared to one another. And then finally, we need this continued sort of Tropomi S5 type coverage in the afternoon, and this really sort of goes out to ESA to hopefully put something up after a Tropomi or extend it, because then we'll get these 2 measurements a day, and this will tell us actually something about convective cycles, which will be useful. Ooh. That's it. Thank you.
Thanks, Tim. Questions from the audience? Curiosities? If not, Diego has one.
Yeah, well, first, thank you so much for the talk. It's great to see the atmosphere represented. I think that we hydrologists often forget that the water cycle is a cycle. My question goes more in the direction of water vapor origins. You know that there are plenty of Lagrangian and Eulerian models tracking water vapor in the atmosphere. Maybe just even if it is land versus ocean origin, can the isotopologs actually help you with that?
Yes. So this is an idea that I've been discussing with ESA recently. So the idea is you could build classifiers so that because you have this 2-dimensional data space, the easiest way would be to build a classifier and then start to analyze these. So you have these curves and they tell you something about where it's come from, or the source, and then something to do with the age. So you probably also need some sort of Lagrangian type to track as well, but the exact details of this is still to sort of be figured out. But the answer is yes, and
yes,
to show that we don't
maybe a quick follow-up is a bit unrelated, but is there any hope to use all the balloon sounding data we have of profiles of humidity in the atmospheric boundary layer and beyond for validation, or you cannot really relate it easily?
So the current sort of profile information we have gives us information about the humidity, but what we miss is this this fractionation profile.
Right.
But the combination of the satellites start to give us a couple of points along that sort of that profile, potentially with Forum as well. With the far infrared, we may get another point nearer the tropopause. it's all very, very new, but we're now in the era where the observations can now keep up with the models and maybe offer new information. So it's sort of a revolution time. Yeah.
Really interesting. Thank you so much, Tim. So you want to take over?
Oh, it's the same. So now last contribution of this block. It's from Nicolas Tabouret. Topic is Sentinel-6 and inland waters.
Good afternoon, good evening, everyone. So I'm Nicolas Tabouret. I'm going to present you Sentinel-6 microfilage performances assessment over inland waters during its tandem phase with JSON-3. So we are back to altimetry, and just a teaser for you to stay until the end. Quite late, we are developing an innovative method to validate SAR data. So big thanks to my co-authors, Samira Amraoui, Thomas Moreau from CLS, and François Boy from CNES, with whom I had an interesting discussion to set up this talk. So Sentinel-6, as you know, was launched in 2020. It's part of the Copernicus mission, so it means it has an essential place within the Copernicus services alongside other altimeters such as Sentinel-3. And Sentinel-6 has been integrated into in some Copernicus services that are of interest for us in hydrology, namely the Copernicus Global Land Monitoring Service and the Copernicus Climate Change Service. So these downstream services need some feedbacks on the quality of the Sentinel-6, Sentinel-6 missions. Hence, this study over the tandem phase that was set up by the ESA Sentinel-6 JTEX project. So to ensure the continuity of the TOPEX JSON historical series, we need some important information. For example, understanding the intermission biases in between the missions, for which tandem phase are great, and also switching from a low resolution mode, conventional altimeter JSON-3, to delayed Doppler altimeter. So whose footprints are very different. Tandem phase are essential to understand the difference in between the missions. So long story short, during the tandem phase with JSON-3, several modes were activated on both Sentinel-3 with several patterns of observation. So what's important to remember is during the commissioning, there were observations in low resolution mode of inland waters. So for exact comparisons with JSON-3-like altimeter. And then since September 2021, the altimeter was switched into SAR mode over land. So we also performing comparison on that. And we also took a benefit of some special mode that was activating during the commissioning, the LX mode, for which we have both LRM and SAR data that were transmitted back on the ground. So here quickly a reminder of the objectives of this study. So most importantly, characterize the differences, validate those data over inland waters, and push towards new products, innovative methods to improve the quality of water level monitoring over rivers and lakes. So first, quickly to start with the LRM for Sentinel-6, so which was used over land only during the commissioning phase. So this is to point out a pitfall that also appears in some of JSON-3 data, but to a lower extent, is the clipping of some waveforms. So when looking at the nadir of some water bodies, the waveforms are clipped, saturated if you prefer, and the impact of which is that that the retracking, especially with threshold retrackers, are trapped in the leading edge of the waveform, and the range is strongly underestimated, which leads to overestimations over the water surface height. In this example, for example, 4 meters. So one of the part of the study was to quantify how important this this effect is. So we perform a data extraction over lakes and quantified the occurrence of such clipping as a function of the transect length, the crossing of the satellite ground craft with the lake, or if you prefer with its size from 300 meters to 15 kilometers. So the average percentage of clipping is 30%, but it's really important on small water targets and decreases when looking at larger water bodies. The results on rivers are quite similar. Quantifying the biases in between the mission was one of the key objectives of this tandem phase. So in between Sentinel-6 and JSON-3, we exploited this tandem phase by, I would say, coupling, collocating points that observe the same water bodies in the same space and time positions. And we compared the water surface height estimated with both. So here you have a distribution of the difference of the surface height. So we see very interesting results once we remove the clipped waveforms with a bias order of 2 centimeters, which is, I would say, good result and expected as the technology in between LRM is in the same on board as the both mission. The real world strength both by Sentinel-6 is this SAR mode. So let's quantify the bias in between SAR and LRM, exploiting this LX mode that happened during the commissioning phase that I mentioned in the introduction. So what we did is that we compared the water surface height obtained in LRM and SAR at the same position, of course, and plot the histograms. But we perform that as a function of water body sizes. When you take big water bodies, long transects, what you observe is that we have a 9 centimeter bias in between the SAR and the LRM estimates. This is due to the difference in the footprints in the waveforms that are produced by the altimeters. And when going to smaller targets, you see that we are switching towards more negative values going down here. And when looking at the smaller water bodies, very small lakes or rivers, the bias goes down, and the bias in between SAR and LRM is of the order of minus 24 centimeters. So this is an important result. The bias in between conventional and SAR altimetry with OCOG retracker will be water body size dependent. And then what we wanted to do is quantify the absolute precision of the retrieved water level. So to do so, we used a method that was developed in another ESA project, namely StreetArt. So the idea is to compare the water level time series obtained from Sentinel-6 data with in situ water level time series. So to do so, we need to define, namely, virtual station. So at the crossing of the satellite theoretical contract and the river, and we want to reconstruct the altimetry, the water level time series here. Using successive passes of the satellite, we extract the data at the nadir of the river, or as close as the nadir as possible. As you've heard a lot since the beginning of the week, rivers are slopy. And this is a representation of the distribution of river slopes over this world database. So as you can see here, the median value is of the order of 60 centimeters. Sorry. So as the satellite contract is shifting a bit in between 2 consecutive passes, this river slope has to be accounted for and corrected, mainly repositioning all data at the center of the virtual station. So this is accounted for in the processing. Another element, I'm not going into detail, but slope also has a geometrical effect at the position of the closest return of the signal, which also affects the estimated water surface height. So this was accounted for in the analysis too. Then you select the data of your closest in situ station and accounting for some propagation time here, you extract the in situ data that correspond to the moment of your satellite pass over the virtual station. And finally, you can compute the metrics that will give you the performance of your altimeter, namely, to assess the accuracy of the mission, namely the bias or RMSE, to assess the precision, the unbiased RMSE. You can also compute correlation and percentage of valid data to have an idea of your number of outliers. So here are the results when comparing Sentinel-6 SAR mode, water level time series, and JSON 3.1s with the in situ time series. To do so, we divided the stations at which we are doing the comparison into 3 classes. The simple ones, flat canals, very simple. This removes a lot of slope issues mainly. Here are the results of a canal in France using Sentinel-6 data with OCOG retracker. So the correlation is very good. The bias is of the order of 14 centimeters. And something very interesting, the precision assessed by the unbiased RMSE is of the order of 2.3 centimeters. When comparing to JSON 3, the precision is of the order of 16 centimeters. Here you can see the full benefit of SAR mode. Going into more complex rivers, some of them are having slopes, that's class 2. You see that the precision for both mission degrades, which is 30 centimeters for JSON 3, and we cannot attain anymore the perfect precision that was obtained with Sentinel-6. Going into even more complex cases, such as on this one, on which you have a step on the river, both missions basically have the same precision compared to in situ, which means that these complex cases really have to be fully understood to fully benefit from the potential of Sentinel-6. But, and this is where the interest of SAR is, SAR footprint is, as you saw on the first slide, is basically a band here. Extracting the altimetry data, what is usually done, is extract them at the nadir of the river. They're all along the river. We have to account for slope, and they can be contaminated with surrounding water bodies. Exploiting the SAR-bound footprint, we decided to extract the data in the SAR-bound. They are not at the nadir anymore, but they are all their SAR-bound for each cycle are targeting the in situ position. That's why you can reconstruct the in situ, the altimetric, water level time series at the exact position of the in situ. So the comparison is easier. You do not have to account anymore for the slope or other correction, propagation time, etc. When doing such treatment for this river station, the precision improves from 12 centimeters down to 3 centimeters using Sentinel-6 data. Of course, usual nadir virtual station don't have to be getting rid of. This configuration is not always efficient, especially in the case where you have other water bodies under those points. Obviously, they will measure this and not this. But this method of processing of nadir data, so that François Boy also mentioned you yesterday with this very visual Garand case, we can now define new station and measure, establish water level series over rivers at position where it was not previously possible. For example, in some cases where the ground track is parallel to the river or almost does not cross it. In very complex cases with meandering, where would you have defined here the station? Here you want to define it off nadir just to intersect one branch of the river to reduce contamination. You can either shift it at a more suited place to avoid all these contaminants that are in the SAR band. Exploiting this new definition of virtual station, we investigated how we can fully benefit from the SAR precision, integrating some new treatments. So the first one we considered is amine processing. So we used the SMAP processor to do so, and reprocessed Sentinel-6 L1B and L2 products, introducing this filtering into the processing. Basically, this filtering is reducing the side lobes by applying such filter on consecutive measurements, and then more best focuses the signal within the Sarbon, removing along the track contaminations. A comparison with respect to in situ was performed over 12 stations using the French network. Here to summarize, I represent the URNSE, so the precision and the bias with respect to in situ. For the official L2 products, the bias is of the order of 21 centimeter, unbiased RMC, so the precision 9.8 centimeter. Once the amine is integrating, as you can see here, the precision improves a bit. The bias is mainly due to the retracting algorithm that is used. We have more than 20 centimeters here with OCOG. We also tested the sine square bias in this analysis, and you see that on top of the precision improvement due to amine, we have a very significant, almost zero bias using this retractor. So this is an important result of the study too. Of course, all NOT stations have very, very good performances. You can see I let very complex stations here. Amine is not solving everything. In some cases, we still have waveforms with several peaks. And the retractors, when they retract the one peak, you cannot do anything. This is not anymore a question of precision. This is just a retracting error. So to do so, another method that can be applied is fully focused SAR. So this consists in the coherent processing of all the pulses that are returning for the same target, and this helps improving the resolution in the along track direction. So we are really expecting improvement in precision, particularly for a complex target for which contaminants were falling in the Sarbon before, and now with this very thinner pattern along the track, we expect a reduction of the improvement of the precision. Sorry. So 18 stations were considered. We studied over 10 simple configurations, the same 10 as in the slides before. Results are presented here in terms of precision. There is not much improvement when switching from unfocused SAR to FF-SAR. Bias is still around 0 since we use the sine square processing. But when you are looking at very complex cases, such as this one present here, where the Sarbon could be contaminated by meanders, using fully focused SAR altimetry, you better focus your study on a particular point of the river. You remove this along track contamination, and there you can see once again the full benefit of the precision of the SAR altimeter on board Sentinel-6. Of course, not all complex cases can be, very complex cases can be solved by FF-SAR. We are currently working on new methods, and I'm not entering into details. I'm inviting you to follow Jean-Alexis Daguzet's talk tomorrow, in which he will discuss how all these complex situations with several peaks can be handled. So to finish this presentation, some take-home messages and recommendations. So I'm not coming back on the results from the clipped waveform on the LRM. I remind you, LRM is not used over land since the end of the commissioning. This is just a warning in case you would go back to this data. We show the full improvement brought by SAR altimetry with respect to the Gen 3 performances, and particularly doing these comparisons with in situ data. We define a new type of virtual station exploiting the very specific pattern of the SAR band to define off-nadir virtual stations that are very useful to do the study at the exact position of the in situ. Then you can really assess the absolute bias, quantify the absolute bias of your water level series of your mission. The improvement brought by the sine square retracker were shown, particularly into reducing this bias. And complex cases benefit for SAR altimetry and benefit from some treatment that can be applied on it, namely ramming, and to go even further, fully focused SAR, that you already saw some results yesterday. In this case, precisions better than 10 centimeter can be obtained with Sentinel-6. So we see we are entering into a centimetric precision of inland water too. Recommendations. So we stress the importance of long enough tandem phases in between the missions so that several cycles can be used so that we have several points on this water level time series for the different positions. Amine processing has been shown interesting and could be something integrating into the operational processing. We stress the importance to continued R&D to exploit the off-nadir signal in altimetry, to develop multi-peak retracking algorithm. And another message, I had no space left to write it here, but as you can see, reaching centimeter precision, the retracking error is not anymore overwhelming the error budget in altimetry. So all these other components, namely the atmospheric correction that have to be accounted for to the precision altimetry, are now taking more and more importance into the error budgets, and this is definitely something also to work on in the future. Thank you for your attention.
Thank you so much, Nicolas. Are there any questions? I see.
Thanks, Nicolas. Very nice talk. I have a fundamental question. Why there should be a bias between Sentinel-6 and JSON-3?
Why should there be a bias in between both missions?
Yeah.
As I mentioned, so this is, go back to the first slide, their footprint is different. JSON-3 is a conventional altimeter. It basically integrates the backscatter signal within this big footprint. SAR processing basically focuses the backscattered energy from this band. So the waveforms, the backscattered energy at a function of time, do not have the same shape for LRM and SAR altimetry.
So that means if you have a lake, there shouldn't be any bias. So if predominantly the water is reflected from water surface, so the bias should be zero.
Yeah, you have a bias if you apply the same kind of threshold retractors. Threshold retractors are empirical. A threshold is set up to position the leading edge in the waveform. So this is empirical. And the message is that when you compare both and use a constant threshold retractor such as OCOG, as the waveform is evolving, as you are comparing smaller or larger targets due to surface roughness or water body size, this threshold retractor do not behave the same in LRM and SAR.
That was actually the background to my question. Actually, so what you see here is the retracker performance is not necessarily the bias between two missions. So it's actually, so you applied OCOG to a SAR, which might not be suitable, and then you get the sort of not perfect result, and then that's a retracker performance.
Exactly. This is retractor dependent. And if you use the operational product with this OCOG retractor embedded in them, you will notice some bias with such shape in between Sentinel-6 SAR and JSON-3 LMM data.
But Nicolas, you also have that 2.3 centimeters between LRM and LRM.
Yeah.
That is virtually zero. If you imagine that these are two different machines built on ground, and there are two generations of of Poseidon altimeters. On ground, they are also calibrated on ground, so not in space. And then to see that these two instruments only differ by 2 centimeters on a range that is 1,350 kilometers, that difference is virtually zero. Now, you can argue we as EUMETSAT need to make sure that the product in the end needs to be zero. That is what we'll probably do in one of the future generations of the processor, where you make sure that there is no difference between JSON 3 and Sentinel 6.
Yeah, but there was also 20-centimeter bias as well. So
yeah, here the 20-some between SAR and LRM, as Nicola correctly explained, there are two different technologies, two different ways of measuring a very complex scene. One is circular, the other is a stripe. The retrackers, even though they are OCOG, of course, the waveform is totally different between SAR and LRM. So that's understandable. But the 2.3, that's the bias that you focus on. Yeah. That's the one that is coming from the instrument virtually. And that you can argue is virtually zero. There have not been many altimeters in the process, progress between Tilburg, JSON 1, JSON 3 that were so close.
Yeah, this is not I would say, a performance problem. This is just difference in the technology and bias that have to be known and accounted for in downstream services.
You need to know what you're measuring.
Yeah.
But there is one correction that I want to say to you, Nicola. You said that there is no more LRM since the commissioning. No, LRM is on always 100% of the time. Now, then, and still. The SAR mode has changed. During commissioning, in the earlier part of the commissioning, we only had a few boxes. Now we also have globally SAR. So LRM and SAR globally, everywhere, all the time.
Okay, thanks for the...
And that's been so since October of 2021.
Thank you so much. Good. So we're very behind schedule, but we don't need to extend it much farther unless we sense that there is a big willingness from the audience to engage in a discussion. And I presume it's already very late, so we're just gonna plug in there a couple of seed questions, and then if we see that there is no engagement, then we can all go have a beer or whatever you guys wanna have. So given how diverse the set of talks was, it was very difficult to actually come up with coherent questions on a topic. So as you may imagine, the questions we have in there are rather generic. And in fact, we wanted to just kick in and see with the first question that, if I'm not mistaken, is about the uncertainty. So if we think that at the end of the day, we are all working with water and we are interested in a global water cycle, and this is what this conference is about, we understand as well that there are variables that might be more uncertain, perhaps more important than others. If we set a common goal of understanding the global water cycle from a closure perspective, where is the uncertainty in the variables that prevent us from closing that global water balance? So that actually unites all the variables that have been discussed in this session. So that's why I wanted to actually kick in with that and then see if you guys want to discuss that further. So if we extrapolate that question to the energy cycle, I would say, well, it's probably clouds. The biggest source of uncertainty is probably the intake of energy in the oceans. But what about water? I saw a diagram actually in one of the talks of a paper by Wouter Dorigo 2 years ago with the storages and the fluxes of water. If you look at that diagram, it's actually evaporation, which is my favorite variable, and that makes me both sad and happy at the same time. But what is, in your perspective, where we should be putting the energy on if we want to close the water balance from space? What is really missing right now? Where should the funding go? And if nobody wants to take the mic, then go ahead.
Yeah. We actually had kind of the same discussion from the previous. You were there or not?
I was not, but given the structure of the sessions and the diversity of topics, I'm not surprised.
So I just want to discuss one topic that has not been discussed here, but we talked a lot about precipitation. Yeah. Depending the scale at which you're looking at. precipitation maybe contains lots of uncertainty, depending on and different uncertainty depending on whether you're looking at satellite for precipitation, radar for precipitation, rain gauges for precipitation.
And wouldn't you be able to reduce that uncertainty at least at the large scale, temporal and spatial, just by looking at energy balances?
Sorry,
like the top of the atmosphere, like top of the atmosphere energy balance.
Yeah, I know that.
Couldn't you actually use the top of the atmosphere energy balance to reduce the uncertainty on precipitation, given the influence that condensation has?
So you are talking globally. I am talking
Right.
extremely locally. Storm.
Okay. Yes.
Yeah. So, and for that, there have been an interesting presentation showing for very localized extreme events, the storm, the differences between what you can find from satellite, what you can find from a localized weather radar, but also from in situ stations, and everything was different. So your initial questions was, sorry, on what effort could be put to reduce the cycle. Even at global scale, I think that precipitation could be something we should look at, because it's all diverse here.
Yeah, so we still need more precipitation missions.
Probably.
Yeah, yeah, it's a good call. Are there any other comments on this? I'm actually surprised of how much you guys can endure, like in terms of like a long journey today from the beginning of. So if you want, we can close it here. Or I'm not sure if there is anybody that wants to take on the microphone and perhaps bring their own question, because that would be even more interesting than forcing anybody to talk about a specific topic from this side of the aisle. So is there anybody that thinks that we're not talking about some very important theme, and maybe not only in this session today, but perhaps in the last 2 days hasn't been mentioned, and has a feeling that we are just missing that? If not, and if nobody wants to prevent me from doing this, I'm going to close the session, welcome you to come back tomorrow, and thank you so much.